I would like to thank Professor Yang for the kind invitation. It's really my great pleasure and honor to give this talk in this conference. So I'm going to talk something different. My title is Refined Analytic Radius of 3D Navier-Stokes equation. So motivated by the classical Navier-Stokes equation, here we consider the following 3D generalized Navier-Stokes equations. Here, the unknowns U equals U1, U2, U3 denotes the velocity of the fluid. Here, this Q, UU is a quadratic term of this U, which is a linear combination of terms like this. Q, K, L, J, M, D. This is like a Fourier multiplier of homogeneous degree 0 with this derivative partial M act on UKVL. So in fact, if we apply this Laurent projection operator on the classical Navier-Stokes equation, we will recover this generalized Navier-Stokes equation from the classical Navier-Stokes equation. So questions and the motivations. Conventional wisdom, like strong solutions to the speculative system, like SQG equation, Navier-Stokes equation, strong solutions are in fact analytic in both space and time variables. So the questions are like optimal analytic radius of this solution. And a physical implication of this analytic radius is closely related a Kolmogorov type length scale in turbulence. So precisely, analytic radius leads to a lower bound for Kolmogorov dissipation scale. For example, like a Kolmogorov open curve hypothesis, as the viscosity nu tends to the 0, if you define this energy band Ek, like the summation of the indices J minus K less than 1/2, the square of the Fourier coefficients should decay like K to the minus 3 for K less than K star, and a decay like K to the minus N for K greater than K star. But if you suppose the Fourier coefficient decays like exponential to the minus alpha 0 nu times modulus of J, then from this formula, it's easy to observe this K over logarithm of K should be greater than or equals to 1 over alpha 0 of nu, which means from this inequality and this inequality, you'll find that the Ek should be like K to the minus N. So from this inequality and this definition, if we ignoring this logarithm, you'll find that this 1 over K star should be greater than or equals to like alpha 0 of nu. So importance of understanding this analytic radius, like a fundamental length scale for balancing two parts for the viscous effects and nonlinear inertial effects. Practically, this also yields exponential convergence of finite dimensional Galerkin's approximations. And other applications, like sharp temporal decay rates of solutions in high stop-left norms, geometrical regularity criteria, like the work by Grujic and Kukavica. In fact, in the paper, famous paper by Yonlahe in 1934, he pointed out like all the reasonable estimates to the classical Navier-Stokes equation should be scaling invariant and this scaling transformation. In fact, it's easy to observe if this UTX is a solution to 3D Navier-Stokes equation, you'll find the scaled solution lambda, U lambda squared of T, and the lambda of X is again a solution to the 3D Navier-Stokes equation. So we define the critical space if the norms of which are scaling invariant and this scaling transformation. So it's easy to check all the following spaces are scaling invariant and this scaling transformation, like H dot 1/2, L3, and B dot homogeneous space of space with with this indices like -1 plus 3 over P, PQ, and a BMO -1, all these spaces are critical spaces. And this, in some sense, explains you why 3D Navier-Stokes equation is so difficult. Because energy law only gives you this a priori estimate of L2 for solutions of 3D Navier-Stokes equation. But the critical norm is like h dot 1/2. So we needed to gain this one additional 1/2 derivative in order to solve this classical Navier-Stokes equation. It was first proved by Kanamiya-Planchon in 1993, giving each data in this space of space with negative indices, 3D Navier-Stokes equation should generate a unique global solution. The endpoint space in this setting is called a BMO -1. This space contains the norms of which contains two parts. One part is like the norm of B dot -1, infinity, infinity. And the other one is because of 3D Navier-Stokes equation have this quadratic term, you must have this heterosystemic group act on U0 belongs to L2 local. So this regularity plus this scaling defines the constant measure part of this BMO -1 norm. So the endpoint in this direction is like giving each data in BMO -1 to be sufficiently small. This data should generate a unique global solution. This is a famous result by Koch and Tataru. In general, given each data in B dot -1 infinity, infinity, 3D Navier-Stokes is ill-posed. This result is due to Bogan and Pavlovich, and also due to another paper by Beijing. And this solution, Koch and Tataru solution, is in fact analytic as long as time greater than 0. This result is due to Beijing, Pavlovich, and Staflani. Prior arts on analyticity. In this direction, the first result is due to Mezuda in 1967. He proved for 2D Navier-Stokes equation in a bounded domain with directional boundary condition, the solution is analytic and in both space and time. Both space and time. In 1989, Fouillard and Tamang introduced the Jerry norm and proved that in the periodic domain for initial data in H1, he proved that a solution should be analytic as long as time t greater than 0. And then furthermore, this ratio between analytic radius of this ut over square root of t should have a positive lower bound sigma. And Grujic and Kukavica also proved similar result for analyticity with niche data in LP for P greater than D. The main idea of G and K is to consider this complex solution of 3D Navier-Stokes equation. So after this result by Fouillard and Tamang, later the result was improved by Lamaria Hissou around 2000, like giving initial data in h dot 1/2, he can prove the Fujita-Kato solution will be analytic for t greater than 0. And furthermore, he can prove the following estimate. So this estimate in particular tells you this Fourier multiplier e to the square root of t d act on the solution ut should belong to h dot 1/2. This estimate also implies this analytic radius of this solution ut over square root of t should be greater than or equals to 1. So let's go back to the classical Navier-Stokes equation, which can be written in this way. So the Jerry norm means e to the minus t Laplacian square root act on this u in some subleft space of base of space. So why we should study this norm instead of this norm? This norm in particular for the ocean, like in the 2D Navier-Stokes equation, for the initial data, if it's axisymmetric, you'll find this nonlinear term will disappear for the Bautista equation. For in particular, for axisymmetric data in two space dimension, the solution should be for the Bautista for the 2D Navier-Stokes equation. The solution is in fact the solution to the linear heat equation. For this solution, it's called Olsen. The Olsen solution is like e to the minus t Laplacian act on this solution belongs to this space. But here we study this nonlinear problem. This Olsen is too much spatial. So an example is like in space dimension 6, we consider like the following heat equation: partial t of u equals Laplacian u plus this modulus of u times u. For this equation in 6 space dimension, we have explicit example called the Oben-Talenti bubble solution. Ux can be written in this way. For this solution, you can explicitly verify like it belongs to analytic space instead of this e to the minus t Laplacian act on this solution belongs to some space. So I also should explain you this result by Herbst and Skip State in 2011. Given initial data U0 in H gamma for gamma between 1/2 and 3/2, they can prove for 3D Navier-Stokes equation with initial data U0 should have a unique local solution U on 0 to t. And then furthermore, for any epsilon between 0 to 2 gamma minus 1, there exists a small time t0 which depend on epsilon gamma U0 H gamma norm belongs to 0 to t, and also positive constant c such that this e to the exponential 2 gamma minus 1 minus epsilon time composite with square root of t logarithm of t absolute value d act on this ut H gamma norm should be finite for any t between 0 to t0. Because this inequality holds for any epsilon greater than 0, the above estimate in particular tells you the ratio of this lower limit should have this explicit lower bound like square root to the 2 gamma minus 1. So after this result, we have several natural questions. The first one is like the critical case. For gamma equals 1/2, do we expect this lower limit equals plus infinity? The second question is like the optimality of this lower bound of this ratio. The third question is like for gamma greater than equals to 3/2, is it what's the optimal lower bound of this limit? The last question is like, with this improved ratio, can we improve the long time asymptotics of the solution to Navier-Stokes equation? So in order to study this problem, joint work with Jean Schumann and Gallagher, we considered the following semi-linear parabolic system. Partial t of u minus Laplacian u equals pu. Here, this u equals uj, a vector for j between 1 to n. This pj is a nonlinear term with this Fourier multiplier ajld act on this product of this ujlj. So here, this ajld is like homogeneous Fourier multipliers of degree beta between 0 to 2. The order of nonlinearity here, k should be greater than or equals to 2. The scaling to the above equation is like if this utx is a solution to this semi-linear parabolic equation, we find this lambda alpha times u to the lambda squared of t, lambda of x is again a solution to this parabolic system. So for beta equals 1, k equals 2, this system corresponds to the classical Navier-Stokes system. For beta equals 0 and k equals 3, this corresponds to this cubic heat equation. So for this system, we first proved giving alpha between k1 over k to d over k. By the scaling, we can define the critical indices as critical equals d over 2 minus alpha. For initial data in the subcritical space, h critical plus delta, for delta greater than 0, we can prove this equation has a unique solution in the so-called Cartoo space, k t over p, which defined as follows. Furthermore, we can provide a lower bound for the lifespan. So the solutions enjoys analytic smoothing for delta equals 0. There is a dependence on the profile. That will be the next result. So we can prove for delta positive, the solution should be analytic, and furthermore, analytic radius of the solution over square root of t times the square root of this minus logarithm t of this u0 norm to the power of 2 over delta, with lower limit should be greater than or equals to square root of 2 delta. And in particular for delta equals 0, which corresponds to the critical space, we have the following estimate. Because of these properties of heat semi-group act on this u0 and this definition of Cartoo space, norm in the Cartoo space, with this explicit form, in particular, we can prove this analytic radius over square root of t. As t tends to 0, this limit should equals plus infinity. So as an application to 3D Navier-Stokes equation, part A echoes Herbert's skip-state result, which corresponds to like the subcritical case. The critical case, we solve, in particular, solve this problem for 3D Navier-Stokes equation with niche data in this h.1/2. And in fact, in this paper, in the same paper, we can also prove for any global solution, U, which is continuous from 0 to infinity, h1/2 R3, this ratio analytic radius over square root of t, as t tends to infinity, this limit is also equals plus infinity. The reason why we can prove result of this type is because of the result by Gallagher, Eftimi, and Planchon in 2003, where they can prove for any global solution of 3D Navier-Stokes equation, as t tends to infinity, this h1/2 norm of this ut equals 0. So this result is not like, does not contradict with the explicit example of this open talent example we presented before, because this example does not satisfy this condition. So next, a sampler of LP and a Besov type results for estimating of this analytical radius of this UT. So like the result by Lamarier, he saw in 2000 for initial data in LP, for P between 3 to infinity, this analytic radius of this UT over square root of T should have a positive lower bound. And a similar type of result was also proved by P, Biswas, and Tedmore in 2011 with niche data in this Besov space with negative indices. So I also proved with my students with niche data U0 in LP. For P greater than 3, but less than 18 over 5, we can prove this e to the square root of this quantity act on this VT with this suppletive norm should be controlled by the right-hand side. So this result in particular tells you the analytic radius of this VT over square root of T logarithm T should have a lower bound like this. Here, this Vt is in fact denotes the nonlinear part to the 3D Navier-Stokes equation. So here this V equals U minus heat same group act on this U0. So why we expect result of this type? If we denote this V equals U minus this heat same group act on this U0, you'll find that this nonlinear part should satisfy equation of this type. For initial data in U0 in LP with P between these indices, we can prove this V should belong to the subleft space of this type. That's the reason for V, we can apply this approach with the L2 framework. Because this P is very much like restricted in the previous result, later I also proved for initial user in LP. For P between 3 and 6, here this lambda cosine, the symbol equals the summation j from 1 to 3, the absolute value of cosine j. Then I can prove this Fourier multiplier act on this Vt in this homogeneous space of space should be controlled by C2 times t to the minus 1 gamma. So in particular, this result tells you this ratio of this analytical radius of Vt over square root of t times logarithm of t should have a lower bound like this. For this result, because here we use symbol of this type, here we lose the lower bound very much. So the crucial idea to solve this problem is to use Fourier multiplier of this type. Because in the L2 framework, we can use Fourier-Planché theorem to estimate this Fourier multiplier. In general, for the Fourier multiplier, we estimated the LP norm, we have to use Hommander multiplier theorem. That's the reason we have to use Fourier multiplier of this specific type. In fact, in the same paper, we first proved, given each data, in this space of space, we can prove the solution, the analytical radius of this solution should have a lower bound of the type. Then the second step, we prove the nonlinear part, in fact, belongs to some space of space if the niche data belongs to some LP. Then we can use approach of this type to solve a problem with niche data in LP for P between 3 and 6. So status quo before 2024 is like working space niche data in H gamma for gamma between 1/2 and 3/2. This result is due to Herbst and skip state. For the critical space, H1/2 is due to Jan Schumann, Galliger, and myself. For LPP greater than 3 to infinity, with this estimate, this result is due to Lamahier-Hissot. With this space of space, it's by like Bay, Biswas, and Tedmore. For LP with P with this indices is my student and myself. And this space of space, this result is due to myself. So coming up, we have a complete solution for initial data in H gamma for all gamma greater than or equals to 1/2. So this is a joint work with Zhong Li from the University of Hong Kong. We can prove, given initial data U0 in H gamma for gamma greater than 1/2, we can prove there exists a positive time t such that the generalized Navier-Stokes equation has a unique solution in C0 to T to H gamma, and also in the space L2 0 to T H dot gamma minus 1. And then furthermore, we can prove for some delta small enough such that this gamma greater than 1/2 plus delta, such that this E lambda T times square root of T times this absolute value of D act on this UT H dot 1/2 plus delta should be finite with the estimate like this. So here, this lambda T, we have this explicit form equals like square root of 2 gamma minus 1 times 0 as j tends to infinity for some positive time t. And we define this beta t in this way, which equals the minimum of this part and also 1/2 gamma minus 1/2 logarithm of t if this eta t to the minus 1/2 gamma t positive. If this quantity equals 0, then we take this beta equals 1/2 times gamma minus 1 logarithm of t. So here in particular, we have this analytical radius of this ut over lambda t over square root of t should be greater than or equals to 1. Here we do not need to take time t tends to 0 for any t between 0 to t0. So this framework works for all gamma greater than 1/2 instead of this like 1/2 to 3/2. And then furthermore, even for gamma between 1/2 and 3/2, we have a pointwise in-time estimate. So in the previous result, the analytic radius lower bound on the denominator is like square root of t times absolute value logarithm of t. But here we also have log t plus kt. And this kt tends to infinity as time t tends to 0. So this even for gamma between 1/2 to 3/2, this result is an improvement of the previous result by Herbst and Skipstead. So some remarks, like for any solution in this space, we can prove this eta j gamma t tends to 0 as j tends to infinity. This quantity equals 0, which corresponds to the Fourier transform of the solution is of compact supported. And this peculiar scenario does not seem to be easily ruled out for a nonlinear problem. Like for 2D Navier-Stokes equation with axisymmetrical data and with also with initial vorticity with compact support, in that situation, the Fourier transform of the vorticity is of a compact support, and also for this Fourier transform of the solution itself. So here also, in the definition of this beta t, we have taken this minimum of 2 parts. This is to accommodate the situation with initial value 0 has a higher smoothness hm with m greater than gamma greater than 1/2. In that situation, we can explicitly calculate if eta j gamma t should be less than or equals to j to the minus n to the gamma. So we can calculate this quantity should then have lower bound like 1/2 times m minus gamma like times logarithm of t minus c. So in this situation, if m is large enough, we clearly see from this beta t like an upgrade of analytic radius of the amount 1/2 gamma minus 1 logarithm of t. And this part is just for the convenience of the analysis for the definition of beta t. So the main idea of the proof to overcome the difficulty, the barrier, like equals gamma equals 1/3/2, we resort to high and low splitting. In this situation, we observed in order to estimate the analytic radius, in fact, we only needed to estimate the high frequency of the solution. So in this situation, for any Schwarz distribution, we decompose A as a low frequency part plus this high frequency part. And in fact, to estimate the analytic radius, we only needed to deal with the estimate of the high frequency part. That's the reason we define the definition of the seminorm of this U in the XT. We only needed to estimate this high frequency part. And these 2 parts is due to our works and also the work by Herbst and Skipstead. So in this way, we define the seminorm in this way. Why here should be t to the power delta over 2. This is due to the definition of best of space with negative indices. Because the critical norm for classical Navier-Stokes equation is h1/2. So we will add this Fourier multiplier d to the delta plus 1/2. This solution should belong to h dot minus delta. So in this definition of best of space with negative indices, we have to multiply this norm by this t to the delta over 2. So the most crucial part to prove this solution is, in fact, to estimate the following part. We only need to estimate the high frequency part of this nonlinear part. So in order to estimate this part, we decompose this f into low and high frequency, and also this g equals low and high frequency. In this way, we have h high, g high, h high, g low, h low, g high, and f low, g low. But it turns out, if we want to estimate the high frequency part, this low part does not appear. The reason is because of the support of the Fourier transform of two distribution, in fact, included in the summation of the support of these two distribution. Because this product of f times g, the Fourier transform will be the Fourier transform of f convolute with the Fourier transform of g. So for the low part, after Fourier transform, if we only need to estimate the high frequency part, this low part does not disappear. This is, in fact, idea due to Borgen. So with this crucial estimate, the other part is almost like standard, and we also can prove similar result for initial data in the critical space. Which I'm going to skip. So far, we joint work with Dongli. We have a complete solution for initial data in H gamma with gamma greater than or equals to 1/2. Roughly speaking, in this result, we have this analytic radius of this ut over square root of t should have a lower bound of this type. So the next question is like, what about general LP, Sobolev, Besov? We need a completely new set of techniques. So in fact, with niche data, U0 in W gamma, P are n for P between 1 to infinity and gamma greater than or equals to -1 plus 3 over P, we can prove indeed this analytic radius of this ut over square root of t should have a lower bound of this type. So in particular, when p equals 2, this result recover our previous result. In order to solve this problem, we needed to use a completely new set of ideas. So in this sense, we completely resolve the Hilbert and the skip state conjectures without any loss, even with niche data in this W gamma P space. In fact, we can prove more general result. In order to define the working space, we have to recall you like a lead over the Pell theory. We recall a function chi r and phi r with support of this phi included in this interval from 3 over 3/4 to 8 over 3. And with support of this chi is included in a ball with radius 3 over 4, such that for any r greater than 0, chi r plus summation j greater than or equal to 0, phi to the minus j r equals 1 for any r greater than 0. So with this definition of chi and phi we can define the dyadic operator in this way. Delta Ju, which means the frequency cutoff, such that at frequency cutoff, the Fourier transform of this U, of the delta Ju, is supported on an annulus with radius 2 to the power of j. And also, delta minus 1U is also a Fourier multiplier. Like after this cutoff, the Fourier transform of this distribution should support it on a ball with radius 3 over 4. So with this, with the introduction of these dyadic operators, we can define base of space in this way. This S indices means derivative. This P means integrability, and this R means summation with respect to this sequence. So we define a distribution U belongs to BSPR, which means this sequence belongs to small LR of n bar to be finite. We know in general, for function space, we have two types of functional space. One type is like three-body Zorking, and the other type is like Bezoff. For three-body Zorking space, an example is like WSP for P between 1 to infinity, but P does not equal 2. In this situation, it's easy to observe, like as J tends to infinity, and this ID minus SJW, BSP infinity, this tends to 0. So we are going to work in a space which we denote like a P, BSP compact. Compact, which means as the frequency tends to infinity, there is nothing appear for this W. So our result can be stated as follows, like a given data U0 in B gamma P compact for gamma greater than 1/2 plus 3 over P, and with P between 1 to infinity. We can prove corresponds to this niche data there exists T1 U0 positive, such that this solution belongs to C0 to T1 to this Sobolev space. And furthermore, for T between 0 to T1, the space of norm of the solution should be controlled by C times the base of norm of the niche data. And furthermore, we can prove for there exists a T0 between 0 to T1 such that the Fourier multiplier e to the mu1 t square root of t times d ut dot LP norm should be finite for any t between 0 to T0. And then furthermore, we have an explicit form for this mu t. That's the reason we can prove the analytic radius of this solution over like a square root of t times this quantity should have a lower positive lower bound. And we can also prove similar results with niche data in the critical base of space. Because here, this indices is -1 plus 3 over P, which corresponds to the critical indices of 3D Navier-Stokes equation. So the future work is like for the 3D anisotropic Navier-Stokes equation, which means for the classical Navier-Stokes equation, we have viscosity in 3 directions. In the higher space called Ekman layer, there is in the high atmosphere space, there is a boundary layer called Ekman layer. In that layer, meteorologists often modelize the turbulence diffusion with the horizontal dissipation different with the vertical dissipation. And usually, the vertical dissipation is much smaller than the horizontal dissipation. So for mathematicians to study this problem, sometimes we just neglect the vertical dissipation for 3D Navier-Stokes equation. In this situation, we call this equation like the anisotropic Navier-Stokes equation, which is like parabolic in x1 and x2 variable, but hyperbolic in x3 variable. For these equations, we can explicitly calculate for initial data in some space, like analytic in x3 variable and sublift in x1 and x2 variable. With small data, we can prove 3D anisotropic Navier-Stokes equation is analytic for t greater than 0 in x1 and x2 variable. But we need this x3 variable to be analytic. So our recent result this assumption is analytic in x3 variable. For initial data in the classical function space, we can prove for 3D anisotropic Navier-Stokes equation, the solution will be analytic in x1 and x2 variable soon after t greater than 0. So that's our most result for 3D anisotropic Navier-Stokes equation. Because we have this improved analytic radius for 3D Navier-Stokes equation, we are also going to study this long-time asymptotics for the solution of 3D Navier-Stokes equation. So far, we only obtain derive the lower bound of the analytic radius. The question for the upper bound is completely open. And all the analysis so far should be performed in the whole space. So the question, like in a bounded domain or domains with boundary, how to solve this problem turns out to be a big challenge for us. I think I'm going to stop here. Thanks a lot for your attention.
Any question, comment?
Common example for the global solution.
Well, not global, for some boundary.
Some boundary.
How is our he gave some example for Euler equation. Almost for Navier equation.
But that solution is not like purely mathematical. They use like AI for some part.
I think they prove something.
So the results they give me is one part, some part with numerical, like with numerical simulation. It's not purely like an analytical result.
No, I think later they have a proof, but they have a boundary.
Boundary.
They need the boundary to help.
You mean the result by Hamho and also Schwarak? I don't know this result.
You're better expert than me, but I know that Tom gave some example.
I don't know this result.
They did point-wise estimate for Navier equation.
Point-wise?
Yeah.
There is some result on point-wise, like for 2D, there are a lot of results in this direction. In 3D, I don't know.
The questions, if not, let's thank speaker again. So we have 2 minutes, 1 minute break. The second speaker of this section is Professor Cao Huaidong from Lehigh University and IS. The title of his talk is Hamilton every type coach pinching estimate for Ricci solitons.
Thank you. It's an honor to be here for the special occasion, for the special conference. Actually, 45 years ago, I was a student at Tsinghua, like many of the young students back there. But later that fall, the fall of 1981, I was very fortunate, thanks to Professor Yao and Professor S.Y. Chen, that I went to Princeton for graduate study. And then a few months later, in spring of '82, Professor Yao invited Richard Hamilton, as well known, to Princeton IES, given his famous lecture on the three manifold of positive Ricci curvature. So I was newly arrived a few months, had no idea of differentiation, very little background. So I thought that would be was thinking that must be have 3 manifolds of positive Ricci curvature. So halfway through, I was saying, haven't seen the first example yet. So you see how ignorant I was in my first few months. But then shortly after that, Professor Yao asked me and Ben Chao to present, give us a few weeks time and start to present the Hamilton's paper. And as Liang said, he asked Gerhard, but Gerhard was already got a PhD. Anyway, that was really a challenge, but really put us on learning the Ricci flow. So, and then things come one after another. By the end of that year, December '82, I passed the so-called general exam, oral exam in Princeton. I saw Professor Yao. I said, Professor Yao, I already passed this general exam. He said, good. Now look at the Ricci flow on Kähler manifolds. So he assigned me this problem, and by then I know remaining geometry, but very little, basically nothing about Kähler geometry. But fortunately, Calabi came under Professor Yao's invitation, and Calabi came give 1 semester essentially a course on vanishing theorems in Kähler geometry. So that was very fortunate. Anyway, that during that period in Princeton and then San Diego, really fortunate to learn geometry analysis from the founders and masters, not besides Professor Yao, Professor Rick Shen and Leon Simon, but Professor Shen actually given many courses, positive mass, Yamabe problem, and other things, and of course also Richard Hamilton. So I'm really grateful for all my teachers. So today I'm going to back to the topic. So I'm going to talk about a type of curvature pinching estimate started by Hamilton and Ivy for 3 manifolds. And that played a significant role in the 3-dimensional Hamilton-Paraman's theory of Ricci flow, as we're going to explain it. And so the question is how this key estimate possibly can be extended to higher dimension, particularly dimension 4. So let me start. So the talk is we're going to present some recent joint work with my former PhD student Jim Xie on 4-dimensional, a few 4-dimensional Hamilton-I type curvature pinching estimate for ancient solutions to the Ricci flow. And also more surprisingly, that ancient solution we expect to have some kind of curvature curvature pinching improvement. But for expanding solitons, seems nobody has anticipated or expected. So out of we were very surprised that actually they were also the type of curvature pinching Hamilton IV type for sons and hopefully immortal solutions, because we'll see from the proof later on why ancient solution is more natural. So the outline is we start with the singularity formations, finite time singularity formations in the Ricci flow, the background, and then we talk about the original version of Hamilton IV curvature pinching estimate and its extensions, particularly one by Binglong Chen in 3 dimensions, and then we going to mention the 4-dimensional the curvature pinch estimate for ancient solutions, and the last we're going to describe what type of curvature pinching estimate we can gain for asymptotically conical expanding Ricci solitons in both 3D and 4D. Okay. So so well known, of course, the Hamilton's Ricci flow equation in his 82 paper, deforming the metric by the -2 of Ricci, and short time existence is either on a compact manifold or complete manifold with bounded curvature, then the solution always exists for a short time, and that is in the compact case due to Hamilton and de Turck, and also solutions unique. In the non-compact case, the existence was established by Wang Shangxi, Su Wanxiong, and also Professor Yao's students, one of the early ones working on the Ricci flow, done many fantastic results on complete manifold. And the uniqueness is established by Binglong Chen and Xiping Zhu among the solutions that have bounded curvature. So you may have unbounded curvature, but as long as the solution has bounded curvature, then it's unique. And the long time existence was established by Hamilton. It says the solution will continue to exist until either you have infinite time or finite time, then the curvature will blow up. That should be limb soup. So the curvature will blow up as approach this finite time. So in this case, we say the Ricci flow develops the finite time singularity at T max. And Hamilton further classified that the finite time singularity into two types. So it depends on the rate of blowout. Type 1 is typically like sphere shrinks to a point or cylinder, as Gerhard in his like in the mean curvature flow, and the other is type 2. So here is already you've seen from Gerhard's talk the other day that the nap pinch, and actually this is pointed out by Professor Yao to Hamilton, and that pink, as long as if we don't have positive ridge curvature, the nap pinch will happen. And that actually is advantage to do surgery and break up the manifold into pieces and start moving again. And then also we saw, as in the mean curvature flow, you have the Janak pitch. And in this case, the blow-up limit is translating, in our case, is steady, which is solitons. In the previous case, that is it's like cylinder, so that's shrinking, which is solitons, we say. Okay. All right. So in general, we when singularity blow-ups, we do rescaling. So that zoom in and slow motion, so we can try to understand, analyze the singularities. And the theory of Hamilton, the paraman, saying that under the parabolic blow-up limits around the finite time singularity, first of all, you always get the ancient solutions as the blow up more that puts time back into infinite minus infinite. And in particular, the type 1 respectively, or type 2 singularities are typically modeled by so-called gradient shrinkage solitons, or in the type 2 case is steady solitons, which is solitons. So what is, let's quickly recall what the definition of gradient Ricci soliton is. So essentially, that's extension of Einstein matrix. So in this case, we'll have Ricci plus Hessian of a potential function is proportional to metric, and shrinking if the constant rho is positive, steady rho equal to 0, expanding rho less than 0. Okay. So the significance we can quickly summarize. And first, I would see is already the extension of Einstein manifolds, or we can view it as special smooth metric measure spaces with constant Berkeley-Emery Ricci tensor. And for us, study Ricci flow, this gives rise the self-similar solutions. So if you have a Ricci soliton, then you can, using the vector field coming from the potential function gradient, and you rescaling, and you also do diffeomorphisms. You get one parameter family of self-similar solutions to the Ricci flow. And most important, of course, the model possible finite singularity models of the Ricci flow. Or long time in the expanding case, it's long time behavior of the Ricci flow. And it's also very closely related to these the important Lee-Hamilton differential Harnack inequality. Actually, Hamilton found the quadratic expression by examining the expanding solitons and looking for quantities. And also there are critical points from variational point of view of parameters, lambda mu entropy, and in the expanding case is the Feldman-Newman-Knee entropy extension. So yeah. So I want to point out that there are three key estimates especially in the three-dimensional Ricci flow that made Ricci flow powerful and be able to, get the results that we all know, the topological applications to the Poincare conjecture and the Thurston's geometrization conjecture. So the first you already heard from Professor Yao's talk, and that is the Lee-Hamilton differential Harnack estimate of differential inequality, and that is proved by Hamilton, inspired by Lee and Yale's work on the heat equation that's in the 93 appeared. And that is valid for all dimensions. However, it requires a strong curvature condition, requires a curvature operator to be non-active and bounded. So you might say that is very restrictive. However, in three dimension, we'll see that it will come automatically you have when we study singularities. So, and that is because of Hamilton-Ivy's curvature pinching estimate. So this is only for three-dimension, requiring the curvature to be bounded. You have complete solution in three-dimension with bounded curvature, and then you would have this phenomenon. And of course, there's also parameters non-collapsing estimate, which is crucial. These are really three fantastic, amazing estimates. And that is the power of geometric analysis really playing. So let me first very briefly recall what the Lee-Hamilton inequality is, and here we are only taking a trace version, so that resembles Lee estimates. So the DDT of scalar curvature plus scalar curvature dot with any vector field plus twice of Ricci acting on the quadratic VV is non-active. And this was obtained by actually looking at the matrix version, rather complex expression. And just before we move on to the significance further, Simon Brenner was able to weaken the non-active curvature operator to something called the PIC2, which implies a sectional curvature has sign, and also it's evolving, preserved under the Ricci flow. And the corollary is from the trace Liao Hamilton inequality is, in this case, the scalar curvature is pointwise, non-decreasing in time. So this is the current time controls all backward in time, and that is very powerful a priori estimates. And if it's not ancient solution, then you have what Miles mentioned, it's T times R is monotone, right? So in this, but ancient solution case, it's just scalar curvature itself. Okay, so I'm going, before I mention the Hamilton IV one, the estimates, we all know that the Ricci flow tends to favor positive curvatures in the sense that the most notion we know about positive curvature are some of the notion positivity, particularly this is due to the evolution equation of curvature. So for example, scalar curvature is in this relatively simple form of reaction diffusion equation, and Riemann curvature operator is more complex. So the right hand side, the Riemann square and Riemann sharp. So in any way, the scalar curvature non-nec by maximum principle or tensor maximum principle, the scalar curvature is easy to see preserved in all dimensions, and Ricci curvature is particularly only for dimension 3, and curvature operator is preserved for all dimensions. And those were Hamilton's early works. And there's one more very important notion called positive isotropic curvature, and that turns out to be also preserved for dimension n bigger than equal to or equal to 4. And first by Hamilton in his paper on 97, and then subsequently many years later by Brender and Chen and Yuan independently for high dimensions. So I come back to positive isotropic curvature because that is an important notion. Yeah. So now let's look at the curvature operator equation, and Hamilton has a maximum principle essentially also saying the PDE is governed by ODE. So it's critical to study the ODE of D Riemann is equal to Riemann square plus Riemann sharp and see how it behaves. So fortunately, in dimension 3, we all know, or if we learn the remaining geometry, the curvature operator is essentially equivalent to the Einstein tensor. So you can, curvature operator is quadratic form, bilinear form, two forms. And if we diagonalize Riemann into three principal curvatures, lambda mu nu, then the Riemann square is just matrix square. So that's lambda square nu squared. And Riemann sharp is essentially, using the algebra of SO3, which is cross product. And so you got those other terms. And so the ODE is actually quite nice in some sense. So by exploring this ODE of the Riemann, Hamilton and Ivy Thames found this, it's indeed quite magical that this estimates. So it says if we have a complete solution to the Ricci flow on three manifold, and suppose we bounded the curvature, and if we norm, and we have eigenvalues of Riemann curvature operator, lambda bigger than equal to mu and bigger than equal to nu, and normalize it by a scaling metric to, say, at time t equal to 0, the least eigenvalue nu is bigger than equal to -1. Then at all points and all future time, we have this estimates. So now the scalar curvature is essentially the sum of three principal curvatures. And that's on the right, on the right-hand side, we have the quantity which is really the first term, minus nu times log minus nu. That's really by exploring the ODE that they came up. This really quite amazing inequality. Right? So what's the consequence? The consequence is if the least eigenvalue nu go to minus infinite, then the dominant one, lambda, is essentially, if it's possible, be controlling scale curvature. Then the largest one will be on the order of minus nu times log minus nu, which is growing up even faster, right? So this is positive curvature. So if curvature is going to blow up, then positive curvature blows up much faster than the negative curvatures. And as a result, when you do rescaling by the maximum curvature or scalar curvature, the limiting ancient solutions will automatically have non-active Riemann curvature operator. And that would provide, of course, first for the Hamilton inequality, have this condition, and plus the geometry of non-active curve, the free manifold. And so those two actually will play tremendously, role that we have. Yeah. So anyway, so that is the role that Hamilton-Ivy curvature pinching plays is in when you dilate in the singularity model, we automatically have non-active sectional curvature all the same dimensions free as curvature operator. Yeah. So are there any questions before we move on? Yeah. So, and of course, what we talk about is dilation limit. So the ORB singularity model of ancient solutions have the non-active curvature operator. And Bill and Chen were able to extend this to all ancient solutions. Doesn't have to come from singularity models. And also, more importantly, that the method of proof turns out to be applied rather general cases that allow us to try other such theories. And I want to say, of course, this results say any three-dimensional complete integral solution that a non-net curvature operator plays all the classification in 3D case. For example, in the extreme solid case, myself and Bill Chen apply extreme parameters results that requires non-active and bounded curvature. So this case will be automatic. And also in Brandless classification, three-dimensional grade studies are claim that I even though Para didn't write even one line how to prove it, but so the proof was provided by in the non-collapse case. In the collapse case by Eli, essentially confirm Hamilton's conjecture about flying wings for speedy solitons. Yeah. And then more recent classification of ancient solutions by Brenda Todidas Phillips and Natasha Session. And also the second remarks is for higher dimension, the ancient solution still can gain something, but rather, that is the scalar curvature will be automatically non-active, but nothing more. Yeah, we have examples. Scalar curvature is non-active, and Ricci already changes signs, right? And also we have extension, three-dimension, the tensor vanishes, so you can also extend to or locally conformally flat ancient solutions curvature operators non-active. Okay, So that is three-dimensional. So he yeah, mentioned the solutions, particularly including streams from solid and solid. So naturally, the question will be what we can do. And fourth dimension is still special, not quite as the curvature algorithm as simple as three dimension, but still very nice. We have the well-known decomposition into cell-to anti-cell-to forms, and as accordingly, we have curvature decomposition into blocks. So you get the Riemann on the cell blue part is the Riemann plus, which essentially is given by the cell blue wire tensor plus multiple scale curvature. And you have traces Ritchie tensor, the off diagonal. So you got A and C and B decomposition. These are earlier decompositions. And trace of the A and C is essentially given by scalar curvature. Okay. Now, here actually the positive isotropic curvature notion in general is looking more complex, but in four dimension, as not well known, turns out the positive isotropic curvature or PIC is equivalent to the matrix A and C are both two positive. That's the A and C. So A is on the Riemann reciprocal on cell blue map to cell blue, and C is anti-cell blue to anti-cell blue. And those are two positives. So it's 3 by 3 matrix. And then you can add a little bit further requirement, say, for the uniformly PIC, and which means PIC plus the largest eigenvalues of A and C, and also the singular eigenvalues of matrix B, because B maps different spaces. It can be controlled by either A1 plus A2 or C1 plus C2, the least one. And then you can talk about Hamilton and the half PIC, that either only A or C is two positive. That's only half of the curvature matrix under that. And Hamilton also, the proof of Hamilton shows that the half PIC condition is also preserved under Ricci is. So in high dimensions, I just flashed here that Miles already explained. So that is the notion that I believe Rick is most familiar with this notion. Okay. So some basic examples. This first here and the top cylinder are PIC, and actually they are uniformly PIC. And CP2 significant was in the classifications of, say, four manifold or high dimensional. Start with the color more that they introduced the notion of pick and show that compact manifold simply connected ones with pick is articulomorphic to the sphere. And then the fourth dimension, Hamilton started in 97, followed up by Chen and Zhu, that they classified compact four manifolds with pick condition, but under some assumptions, no essential decompressible 3D space form, and then they have a diffeomorphic classification. And later, that restriction was removed by their collaborators. Basically, we have a complete classification in the smooth category of compact four manifolds with positive isotropic curvature. Okay. And of course, the pick condition played an essential role to celebrate the work of Chen who they approve of for quarter-inch differentiable sphere theorems. Sorry. Okay, I hope you feedback you can hear. Actually, didn't hold on. So now I'm going to mention a problem that Hamilton cared deeply. I heard he mentioned this problem to me and maybe a few others, at least 15 years ago. And then, right before and during COVID, when I go to Columbia to visit him, every time, but not so frequent as before because more space to visit, he would bring up this problem to me as if that is the first time brought. So after several times, I felt that I must do something about it. So let me tell you what the problem he had in mind. So first of all, let's recall we have the scripture decomposition, and there's a work of Taubes in 92, which says for any compact-oriented four manifold, you can grow on a CP2 bar. You add connect sums of CP2 bar sufficiently many times, then you can make it the self-dual or Vibe tensor, for example, be 0. So based on that, and also the four-dimensional classification in the pick case, so Hamilton asked this question or suggest to study this problem is study the region flow on compact four manifolds with half-pick and use the Ricci flow to, possibly classify all such manifolds. So if that's possible, then you can have immediate application by hopefully, that you can do connect sums. You can start with a compact four manifold with positive scalar curvature, and you do connect sum adding CP2 bars. So in that case, suppose that you can kill or almost kill the W plus you would have, because positive scalar curvature, and you can essentially will have half-pick manifold. And then you run it, and if you can classify the half-pick one, this would give you a stable classification of four manifolds, compact four manifolds with positive scalar curvature. Yeah, so that's the problem that he thought about it and cared deeply. Yeah. And so again, based on the three-dimensional Ricci flow theory, it would be natural, see, if we want to understand the singularity formations and etc., we like to, if there are any curvature pinching properties that we can expect, at least when we have the, say, pick or half pick. Yeah. So actually, Hamilton was the first one to show that on compact four manifold, if we have the pick, then I think you can, change compact to complete with bonded curvature. When the curvature blows up, it actually will pinch towards non-active curvature operator. So in his 97 CAG paper, that is done, and much more elaborate estimates. So turns out that's the case. So particularly if you have a singularity model ancient solution, and if you start with pick, the singularity model ancient solution would have non-active curvature operator. So that's why you can do it. And later, in the work of Simon Brandler, tried to classify higher dimensional static solitons. He observed that the Hamilton's work can be modified under the uniform pick condition. Doesn't have to come from singularity models. Then uniform pick would imply actually should be non-active. There's a typo. Yeah, curvature operator non-active. So in a sense, essentially using the crucial estimates of Hamilton, the thing that you can do that. And that is later further extended to for ancient solutions, essentially parallel argument Yes, still far. So what we can do is either A or C, right? Hopping, either A or C is too positive. So what we can do is saying A is either A or C, well, positive definite. And that's already have some advantage. Well, I maybe mention a little bit later. This joint here, and then another thing is if we assume pick, then besides both A and C are positive definite, we can say something about the Ricci curvature and curvature tensor. The Ricci is too positive. Actually, we expected at least the Ricci to be positive, but technically we missed a little bit. And then curvature operator is normally bounded by scalar curvature. Yeah. And two essential ingredients are involved. One is, again, explore the evolution equations of the curvature tensor. Now, will be essentially matrix ABC, and that is the version. So A, the ODE is essentially A squared plus A sharp and plus BB transpose. And A sharp is the transpose of the adjoint matrix of A. So we can, if we know three matrix, we can handle that. And the key ingredient in all these proofs are Bellon-Chen's lemma by Bellon-Chen, that when he extended Hamilton IV to all ancient solutions is 3D. So it's a parabolic result, and quite interesting. Is suppose we have a solution to the Ricci flow, which is ancient. Ancient is key to our C. So suppose we have a complete ancient solution to the Ricci flow. Notice that there's no curvature bounded curvature assumption. That's the key. You know, if you have bounded curvature assumption, the standard maximum principle argument would work. But key is we do not need to assume curvature is bounded, but instead we have ancient solution. And suppose we have a ellipsis function in space-time that satisfies this inequality. So ddt minus Laplace, the function u is bigger than or equal to a constant multiple u squared. It's important here is u squared, not u cubic like in mean curvature flow. Then in the barrier sense, of course, because then u would be automatically non-active. You have ancient solution, and you satisfy this inequality. The right-hand side is the function squared, essentially. Then the function automatically non-active. And for example, you can immediately apply to the scalar curvature, and then you got the 1 over n to the R scale curvature square. And with Ricci in our case, if you look at turns out the Ricci is too non-active, is essentially same as the scale curvature minus 4 of the largest eigenvalue, single eigenvalue of the matrix B is non-active. And you just compute, and in the end, what we have is the A1 plus A2 plus C1 plus C2. So if you have A1 plus A2 plus C1 plus C2 non-active, then we're done. And of course, if you have weakly pick, that implies that. So yeah, I think we have maybe could explore to prove a little bit more. So that actually is a very powerful, useful lemma. So all Hamilton IV type with only one exception, that his original result does not fall into this category, that the proof doesn't work correctly. And I'll probably just say you do the standard cutoff by evolving distance functions and using Paraman and Hamilton Paraman's how distance evolving distance function the under Higgs equation, how that behavior together with the assumption and plus the standard maximum principle argument, one can get the lower bound of such a form. So you would have some activity. So the key here is now if you put the alpha, which is size going to infinity, and then you would kill this first term. So if you let alpha, the size of 4 going to infinity, you kill that one. And for each fixed t, you let s go to minus infinity, kills the other arrow term. And that is the ancient solution here that helps us to kill the first arrow term. And so that's a brief summary. Okay, I think I have to move a little bit faster. So from the proof, the technical right, you cannot expect anything immortal or expanding solution, without being ancient. So actually, for a long time, we thought that this is Hamilton IV is only really for ancient solutions that didn't. I've mentioned a couple or maybe one with A or C non-active, you can use Hamilton's maximum principle in a way. Otherwise, you have to use Rick and Brandler's Bonnet type maximum principle if you have pick. But the half pick, I don't know whether that can be done or not. So I'll maybe ask Eric later on. So you have complete classification, well, not complete, except the pick case, or the weakly pick, you can be classified in the static case. It could be Calabi-Yau, or the other one, the rich flat and self-dual, or reducible, etc. So what about expanding reaches orthogonals? I think I have 3 minutes. So I'm going to be very brief. First of all, it only works for the result will be on asymptotically conical expanding solitons. And turns out that is most, in the sense, most, way, so far that is the most useful one for us to study. First of all, conic expanding soliton can be instantaneously smoothed out metric forms, and that is Schulze and Faust here had worked on that in 2013, and which is further improved by Chen Li and Piche. Yeah, and the second is that the work of these people suggests that the conical rich expanding solitons might serve to continue the ricci flow past singularity and resolve conical singularities. So not just the long time behavior, but also could needed in the finite time singularity case. So anyway, so this is part of use, and there are examples, not going to say too much. And briefly, we can, for example, let me state one result. That is our recent work with Jimin Xie, saying in 3 dimensions, if we have a reading the expanding reaches soliton asymptotic conical, if the cone, asymptotic cone, has positive scalar curvature, then that expanding soliton will have actually strictly positive curvature, opposite or sectional curvature. So this is like the 3-dimensional analog of Bellon-Chen's result for expanding solitons. Yeah. So, and then I just say all the other results we mentioned in the ancient solutions actually can be carried to the expanding case. And so I'm not going to say too much, and maybe just say what we noticed, that there is analog of Bellon-Chen's lemma in the sense that you can also reduce to on the functions. Basically, it's least eigenvalue of some quadratic form or other things, right? So again, we have a ellipse function in space here, and reading the say expanding reaches automaton, and you satisfy the weighted Laplace acting on U is, in this case, it's not quadratic. You only need linear. Yeah. Linear multiple function U minus another function V, and where we require V to be non-negative. And then we need that at infinity it behaves well, essentially. And that is conical condition in the expanding actually allows this to be automatically true. So once we have that, then we have U will be automatically non-negative. And if V is strictly positive, then U will be positive. So I think my time is here, and I should do open problems. First of all, Simon Bradler and Choi Lee show that essentially for the dimension, if you have uniformly picked, then we'll pitch toward the then solution will be non-negative Riemann curvature operator. And of course, in that case, we also have examples by Eli that has steady soliton, the high dimensional flying wing, has positive curvature operator, but not uniformly picked. So the question is, can you remove the uniform condition or not? And that will be require work, but that'll be more satisfactory. And the second one is if the cone has a pick or weakly pick condition, does that expand to the inside? So if asymptotically to the cone which has a property, does your expanding soliton have that condition? And then study Hamilton-Ivy tension for your model solutions that we're working on yet. Looks like that's possible. And finally, I think this is would be a very interesting question if the well-view really nice. Does the Liao Hamilton inequality or some version of it hold for the mentioned solutions with half pick? And I think at this point we don't have a clue yet, but I think we just want to be optimistic, maybe. So thank you very much, and happy birthday to Liam. Yeah, thank you.
Any question, comment?
Well, first of all, I should comment. Many people do not seem to realize this positive isotropic concept was actually introduced by Silver and I in the pool of Blanco conjecture. When we do the second variation formula for minimal surface, we introduced that. Mario Makarov and more followed that argument, actually.
Okay.
That's the thing about Binglong chance inequality is basically a parabolic version of what Chen and I did in 1974.
Okay.
So you should look into that.
Well,
The right side to
in 1974.
74. First thing I'd like to comment is that if you look at Einstein metric in 4 dimensions,
Yeah.
there are really not many examples of Einstein manifold. There are only 2 major constructions. One uses conformal geometry,
Yeah.
so conformal and Kähler. Basically, all the known Einstein manifold that I know are either conformal Kähler or no others. I don't know.
Yeah. In 4 dimension, I think the yeah.
Therefore, if redshift flow is going to be important in 4 dimensions, one should look at the asymptotic behavior related to conformal and Kähler geometry together. So I think one should look into that much more. Because the asymptotic gradient would be eventually Einstein someway. But of course, you can have some of these big short
Yeah.
So maybe even introduce a concept related to conformal Kähler geometry. Conformal Kähler.
Right.
So I think one should look at the enemies of them in Einstein metric for There's only metric that I don't conform or
That's right. So actually, as I said, is for example, in 4 dimension, the only non-Kähler positive Einstein manifold is the page, which is conformally Kähler, and also the CP2 from 2 points. Yeah. Okay. Thank you. Yeah.
course in UMSC now.
Well, thank you very much. I'm very glad and honored to be here and to participate in this wonderful conference on such a wonderful occasion. Yeah. Happy birthday, Professor Simon. Yeah. And my thanks also to Professor Yao for giving me the stage. So the talk, you see, I'm going to talk about geometric analysis, but my geometric analysis is slightly different. It is based on explicit formulas rather than on estimations. And also the problem which I'm going to talk about is a sort of old-fashioned. Yeah? So it's we will consider two-dimensional surfaces in three-dimensional Euclidean space. Yeah. So very classical differential geometry, and actually rather classical problem. So the question I will investigate here is the surface is characterized by its metric and curvatures. So, and this is joint work with Tim Hoffman and Andy Zagerman-Furnaz. It was published in two recent papers. One was sort of preliminary results about classification of isothermic tori with one family of planar curvature lines, which was required to make progress with investigation of my problem. So, okay, I will start with some basic things in differential geometry. That's usually what we teach at the university in the course of curves and surfaces. Yeah, so classical surface theory. So, but this is just to fix the notations and to explain you the setup. So first of all, we will consider only conformally parametrized surfaces. So it's a map of a Riemann surface to R3. And introduce the corresponding complex coordinate Z here. Well, in terms of this conformal coordinate, the first and the second fundamental forms are written like this, where H is the metric, this capital H is the mean curvature, and Q is so called Hopf differential. So the corresponding formulas for the mean curvature is, of course, a half of the principal curve, half sum of the principal curvatures. So then the mean curvature is defined by this formula, and the Hopf differential is a quadratic differential given by the product of the second derivative of the immersion function multiplied by the Gauss map. So n is the Gauss map here, and f is the immersion function. So we would, yeah, what the classical theory tells us how to describe this surface. Yeah. First of all, these values, the metric, the mean curvature, and the Hopf differential, they're not independent. They must satisfy the compatibility conditions, which are Gauss and Kadat's equation written here. Yeah? So this is the Gauss equation, and this is the corresponding Kadat's equation. And then classical Bonnet theorem tells us that provided these equations are satisfied, then you can integrate the frames, and there exists an immersion F here. So this immersion F tilde, F, which is a map of, not of your Riemann surface, but its universal covering with the corresponding fundamental forms. The fundamental forms determine your surface. So this surface may have periods, yeah? And this immersion is unique up to Euclidean motion. Yeah? So classical Bonnet theory. So if you look at this description, then you see what are the ingredients: the metric, the mean curvature, and the Hopf differential. And they are not independent. They have to satisfy these equations. Yeah. So and then the natural question is maybe you can you don't need them all. Yeah, really. Yeah. So maybe some data are superfluous. And then one classical question which I would like to mention is, of course, this relation between intrinsic and extrinsic geometries. Yeah, whether intrinsic geometry, namely the metric, determines your surface uniquely. Yeah, so there's a lot of investigation in this direction. So locally and globally, I will touch this problem just a little bit. So there are classical results by Dabu. There are global results that claim that if the metric is convex, then your surface is determined uniquely. But generally, it's not the case. Of course, our metric doesn't determine the surface uniquely. Yeah? So it's interesting that okay. Thank you. Yeah, yeah. So it's misprint. Yeah. Okay. Okay, good. So, as I said, many results, many various classes of metrics, and so on. Yeah. So, but there is also a question about analyticity, and I mentioned already that uniqueness was proven for convex surfaces. But if you look at Berger book, Geometry Revealed 2010, yeah. So then he mentions the problem in the section what we don't entirely know how to do for surfaces. Yes, of course, yeah, but not related by the extrinsic isometry, yeah. Okay. So, well, this is mentioned in Berger book, yeah. So it's an open problem, and that's where I've learned this, yeah. Yeah, exactly. Yeah. So the question is, Berger in his book mentions this problem, whether there exist two isometric compact immersions that okay, okay, okay. Okay, so I don't know about this counterexample, yeah, so we should learn. Okay, anyway, it's not the main topic of my lecture, yeah, so we have constructed isometric analytic examples, yeah. So let me say just a few words about this, yeah. So usually when you're lecturing about isometric surfaces that are not congruent, what is the example you're considering? Yeah, you take a surface with a piece of plane on the surface, and then you take a bubble up and then reflect it down, and these two surfaces are isometric, obviously, yeah, and not congruent, yeah. So, but they are also obviously not analytic, yeah. So, okay, but let me pass further to the main topic of my talk. The question is now, do the metric and the curvatures determine the surface? Yeah. So of course, the Gaussian curvature is determined by the metric, but there is also mean curvature. Whether the curvature and the mean, whether the metric and the mean curvature determine the surface. And locally, there are three exceptional cases, and they all were known to Bonnet. These are the cases of constant mean curvature surfaces, so-called Bonnet pairs, two surfaces, and they will be in focus of our research. And those one families, when you have one parameter family of non-constant mean curvature surfaces that are isometric and preserved mean curvature function. So you can develop local and global theory. Local theory is essentially due to, was known already to Bonnet, who has isolated this, who has found all these cases. And the global theory is a new research. Yeah? So amazingly, all these three cases are described by integrable systems, by different integrable systems, but all three of them. Let me just first talk about constant mean curvature surfaces, Bonnet families, and then I will switch to the main topic. Okay, so constant mean curvature surfaces, yeah, where do you see these isometries? If you just take the Hopf differential for your constant mean curvature surface and multiplied by a unitary number, then it's quite easy to see that the Gauss-Kagatz equations are preserved, and then they're so-called associated family of the surfaces. And nowadays, modern global theory of Simpson surfaces was developed. It started with the discovery of these ventators, which we see here in the picture. This surface is remarkable in the sense that it has one parameter, family of planar curvature lines. Yeah, so which you see here. So this is a curvature line, and it lies in the plane. Yeah, so this property will be very important later. Yeah? So it was investigated. After that, all tori were described as through integrable systems by Hitchin, Pinker-Sterling. After that, they were described explicitly, but all tori are described, and nowadays, starting 2010, this higher genus theory is developed further by Hedda with co-authors, and it's more complicated and slightly different. This is an active area of research in global differential geometry. So, second example are Bonnet families. These are the surfaces, one parameter families of deformations preserving the mean curvature, and the mean curvature is non-constant. So, in contrast to other cases, these theories described by ordinary differential equation. And local analytic treatment is due to Hatzidakis, but then there were fundamental papers by Cartan and Chan. So, which and these surfaces were locally classified. Yeah? So later, we've discovered that these equations that appear in this theory are actually Pendevé equations. And then you can use global theory of Pendevé equations to describe these surfaces globally. And this these isometries that preserve the mean curvature, they can be seen on one surface. Yeah? So this is just a sliding along the lines on your surface, one surface. Yeah. So and in particular, what you can see as a byproduct is that the surfaces cannot be compact. Yeah. Okay, now let us switch to the problem of Bonnet pairs. So Bonnet pair is two non-congruent isometric surfaces with the same mean curvature at corresponding points. And in the 80s, it was proven by Lawson tributes that if you have Y2, if you have 3, then you have one parameter. Yeah, so then you are in the case of Bonnet families. So it may happen that you have only 2. So there exist at most 2 compact immersions. That's the corollary of this. Yeah. And actually, for a long time, people didn't know what to prove, whether they exist or whether they don't exist. Yeah, so it was not quite clear. There were even papers that they don't exist, but
this afternoon session, we have 4 talks, and the third talk is online. And the first speaker this afternoon is Professor Tianjun Li from University of Minnesota. Is going to talk about geometry of symplectic log Calabi-Yau surfaces. Let's welcome.
All right, so this is actually the outline of this talk. I studied with Yao, but I'm not a geometric analyst. But I do find geometry analysis essential in what I do. Okay. Maybe we will see that a few mentioning of geometry analysis during the lecture. Okay, so the title is about symplectic log Calabi-Yau surfaces. And so let me begin by reviewing Calabi-Yau manifolds in the symplectic setting as well as in the Kähler setting. And for Calabi-Yau manifolds, I also separate into the high-dimensional case and the 4-dimensional case. There is actually a contrast between these two cases. And then we move on to talk about the log version of the Calabi-Yau symplectic Calabi-Yau surfaces. There are actually a lot of aspects about log Calabi-Yau surfaces. I just mentioned two of those, and then at the end, I mentioned a few applications of the knowledge of symplectic log Calabi-Yau surfaces to other settings in dimension 4. So particularly the symplectic log Kadari minus infinity case. So maybe mention something about weighted projective planes and affine rulings. This is something that's very important and well known in algebraic geometry. Okay. So let me just begin by saying what a symplectic manifold is. Okay, that's just a smooth oriented manifold together with a 2 form called omega that is closed and non-degenerate in the sense that its highest power is a volume form that's agreeing with the given orientation. Okay, so assume M is already oriented. And then I have at least two cohomological invariants in degree 2. One with real coefficients, namely the Durham class of the symplectic form, and then the canonical class of the symplectic form. So to define the canonical class of symplectic form, actually you pick a almost complex structure that tamed by omega, in the sense that you require omega to be positive on any J plane, and such J's are abundant and they form a connected family. So they induce the same Chern classes. So particularly you can define the first Chern class. Then the canonical class is just the negative the first Chern class. So that only depends on omega. And with these two invariants, actually particularly with k omega, I can define what I mean by a symplectic Calabi-Yau, that just vanishing of this integral class. But in dimension 4, actually I will relax this vanishing condition. I just assume that this integral class is trivial in H2 with real coefficient. Okay, so namely it is torsion class with Z coefficient. Okay, the reason is that actually that this this weaker condition does not include, would not include many more full manifolds. Okay, we will see that. Okay, all right. In a higher dimension, I think about 20, maybe 15 years ago, there was a surprising result by Jill Fine and Tony Panoff, who showed that actually there are many symplectic Calabi-Yau 6 manifolds. Beatty numbers, second Beatty number, third Beatty number can be arbitrarily large, and the pi1 can be any given presented group. So the construction actually is interesting, and also it start with the 4-dimensional hyperbolic orbifolds, and then take the twistor space. Okay, the Resnick observed that the twistor space of a hyperbolic orbifold has symplectic structure and actually has trivial canonical class. Okay, so it's a symplectic Calabi-Yau orbifold. But then you can take a resolution of this orbifold, which produces a smooth symplectic manifold. So this resolution actually preserves symplectic structure. And more important, well, in addition, it preserves the Calabi-Yau condition. Right. So, yeah, just on the slide, that actually you can also construct a simply connected symplectic Calabi-Yau 6 manifold that has trivial B3. So it certainly cannot be Kähler Calabi-Yau. Kähler Calabi-Yau has a polymorph 3 form, so it's not trivial. Okay, and you could just by crossing with K3, you can get higher dimensional manifold, or crossing with T2. So, well, if you insist simply connected, you can just cross with K3. So actually, this slide just give you a little bit more detail about this construction. So you really want to construct, many hyperbolic orbifold. It is very difficult to construct compact hyperbolic manifold in dimension 4. It's extremely difficult. Okay. Unlike in dimension 3. But you can construct abundant of 4-dimensional hyperbolic orbifolds. Oh, actually, even any group, you can find one with the pi1. It's isomorphic to that group. Okay, so actually the resolution, I talk about this Crapper resolution, but this is resolution actually is done in purely symplectic way. It's using the local toric structure around the singularities. And there's also compatibilities, okay? And then you do a symplectic reduction. Okay, you after collapsing. The resolution is obtained by collapsing the boundary of the singular parts resolution. And of course, you need to check that the Calabi-Yau condition is preserved. Okay, so that's the story of higher dimensional Calabi-Yau manifold. So you see that they're really, unlike the Kähler case, they're just hard to investigate any classification problem. In the Kähler case, of course, we have the Yau's theorem, the solution to the Calabi-Yau, to the Calabi conjecture. So a particularly nice consequence that is you have the existence of Ricci flat metric, then since metric is Ricci flat, then you have this first Beatty number bound by the dimension. So that's a big contrast. So particularly the fundamental groups really restricted. So they're okay. That's the Kähler's. This is the only slide about the Kähler, general Kähler Calabi-Yau manifolds. Okay. All right, and actually, so Donaldson somehow got interested in studying symplectic structures on K3 surface and like 4 torus. I think that's what his motivation. So then he introduced this almost scalar version of the Calabi-Yau equation. So it looks almost all the same. So you just fix. so you fix all. So you have a So you have a pair of almost scalar form and compatible almost complex structure on this manifold, and you want to solve this equation. Okay. So you want to find a sigma. Okay, sorry. You want to find right. You for any volume form sigma satisfy this equation, you want to find an almost scalar form omega tilde relative to the almost complex structure J. And you want this omega tilde to be in the same cohomology class of omega. And omega, you want omega tilde, the associated volume form to be sigma. So it looks like the same equation, except the J is not assumed to be integrable. Okay, that's the only. But this equation, but this turned out to be much original equation is already extremely difficult. But this equation, this equation is actually it's harder because for non-integrable almost complex structure, you have a 9-piece tensor that really complicated the computation a lot. Moreover, actually, this equation in dimension 6 and above, this system, this is actually a system equation, is not elliptic system. So you may not really get a good handle. In dimension 4, that's Donaldson showed this is actually a elliptic system and prove the uniqueness. And he also demonstrated that if you can prove the existence, then this equation could be very useful to some important problems in 4-dimensional symplectic geometry. In particular, it might be used to approach the question whether every symplectic structure on the K3 surface is scalar. Right, I think that was his one of his primary motivations. But this equation in dimension 4 is also should be also useful to the Donaldson's tame compatible question, whether every tamed almost complex structure is also almost scalar in dimension 4. And just after this, after he defined this, introduced the system, Jasadi, Wang, and Yao studied this equation in the series paper. Somehow they proved some estimates and they got some sufficient condition under under some condition in terms on the positivity of the turn connection, but it's not enough to actually to be applied to study the symplectic problem. Okay, so that's what's transition from higher dimension to dimension 4. So let's stay with dimension 4. So just remind you, a symplectic Calabi-Yau surface is one whose canonical class is torsion class. And then okay, so you see the previous slide. So there's an attempt by geometry analysis to study the symplectic Calabi-Yau surfaces in dimension 4. But at least the ellipticity in dimension 4 suggests you that maybe there's some rigidity in dimension 4, in contrast to a higher dimension situation. Okay, maybe you can prove like some kind of Ricci flat metric in some sense you may have a bounded B1. Okay, not in the Levi-Civita sense in the Ricci flat, but in some other sense, Chen Ricci flat. Okay. But may not directly give you the big number bound, but it suggests you have some boundedness. So for me, I study these symplectic Calabi-Yau surface using Seiberg-Witten equations. And then I also, for the log version, I use both Seiberg-Witten equations and the pseudo-holomorph curve equation. I mean, the results obtained by other people. So first observation is, remember this is just, we just require K omega to be a torsion class, but actually, okay, if B plus is greater than 1, it has, the canonical has to be 0 as an integral class. So this is an application of the Taubes Seiberg-Witten equal to Gromov-Taubes. This is a famous famous fundamental result application. And then when B plus is equal to 1, then either K omega is 0 or it's a true torsion. So this is by applying the Seiberg-Witten wall crossing formula. This is observed by McDuff and Solomon. Okay, so for SC, for the symplectic Calabi-Yau surface, mostly we just use a Seiberg-Witten equation. And there. Okay, so now let me list known examples. So obviously the Kähler ones, symplectic Calabi-Yau, they include, in the broader sense, they include K3 surface, complex tori, or complex torus. You talk about smooth manifold, but you talk about complex surfaces. They include all complex tori, hyperelliptic surfaces, and the Enrich surface. The Enrich surface is not a Calabi-Yau in a strict sense. Its canonical class is a true torsion as a degree 2 integral class. And then another family is given by T2 bundles of T2. Geiger's observed that any T2 bundle or any orientable T2 bundle over T2 emit symplectic Calabi-Yau structure. First of all, emits symplectic structure, and in addition, the symplectic structure has trivial canonical class. And these bundles are classified after diffeomorphism by Sakamoto, Fukuhara, and they have geometric structures like either Niels, some kind of Niels structure, solved structure. This is proved by Masaki Wei. Also, okay, some of them, they are all solved manifolds. And these, they include actually some of the Kähler ones that include T4 and hyperelliptic surfaces. And important things is they're all fibered by T2. Okay, this is actually very, this gives you some hint in how you study, maybe how you try to study, how you try to classify such four manifolds as symplectic Calabi-Yau surface, as a smooth four manifold. But of course, the fibers could be singular, or multiple, or even homologically trivial. So here, very broad, it's just just smoothly fibered by T2. Yeah. Okay, but some of them symplectic fiber by T2 or have a Lagrangian T2 fibrations. Right? But anyway, there always a family T2 filling the only known examples. So around 20 years ago, so Bauer and I independently show that B plus is always bounded by 3. So in higher dimension, this is certainly, there's no such bond. And when B1 is 0, this is actually proved earlier by Morgan and Szabo, this bond. And then this bond on B plus has a lot of consequences. Actually, the first consequence is B1 is bounded by dimension. It's bounded by 4. Okay, and then all the numbers are non-negative, and they satisfy a version of a symplectic Noether type inequality of Fincher, and Stern. And also the virtual first weighted number is also bounded by 4, because if any finite cover of SCY is still SCY. Okay, just so the last property could be useful to study the fundamental group of SCY. The virtual is stronger than first weighted number is less than is bounded by 4. Yeah. And also, actually, you can really identify the cohomology of ring. Okay, it has the same rational cohomology ring as these known examples. So this is what I call homological rigidity. And here is a explicit list of all possible Beijing numbers. And in fact, for K3 type, you have this rigidity over Z. And same for Enriquez. Yeah, not just over Q. I just quickly, I mean, I'm not going to explain all the steps. So this idea of the proof, I mean, the first starting step, we want to bound B plus, right? So I can assume B plus is at least one, at least two. then I already showed that the K omega is 0. That implies the canonical symplectic spin C structure has a spin reduction. And when you have a spin reduction, the Seiberg-Witten equation has more symmetry. So it has the U1 symmetry is elevated to the pin 2 symmetry. And this pin 2 symmetry is very important. And then actually use, so this is Mickey Furuta's pin 2 equivariant finite dimensional approximation to the Seiberg-Witten equation. So it showed the Seiberg-Witten invariant of this symplectic spin C structure is even if B plus is bigger than 3. It's actually, yeah, exactly. When B plus is 3, at least 4, I can show that this value is even. Certainly, it's not true if B plus is 3. I cannot prove this is even because K3 has B plus equal to 3, and this value is 1. So it's sharp in that sense. And then finally, you just invoke that actually, okay, so the above argument doesn't actually doesn't use symplectic structure. I mean, the only place I use symplectic structure is the spin reduction. It's the spin reduction, okay, sort of. And then that will if it's symplectic, will contradict the Taub's result that the Seiberg-Witten invariant of the canonical spin structure is plus or minus 1. So just here, the Seiberg-Witten invariant, the equation is very useful. Okay, although I don't do any estimate, but see that I use. Okay, so here is like the standard speculation, the smooth classification. So it's just saying that there's no exotic SCY. And actually, a particularly interesting case of the test is you look at all degree 4 symplectic hypersurfaces in CP3. Very simple, okay? Just representing the 4H, any symplectic hypersurface is CP3, representing the class 4H. Is that diffeomorphic to K3? That's not known. I mean, suppose that seems like an approachable problem. Okay. Let me say something about, okay, this is about homological rigidity and speculation and smooth classification. Then let's think about symplectic structures. So I introduced some, some spaces and some groups. And so first, this big omega now denotes the space of the all symplectic forms compatible with orientation. And then it projects down to a open set in H2. And then let's take the moduli space. It's just quotient out omega by the orientation preserving diffeomorphism group. And let's take out, let's also look at the action of the diffeomorphism group on cohomology. So with this, I have to say a few questions. So is this, so the CM, what I call symplectic cone, is actually a cone of the classes of a positive square. This is true for all the known examples. Okay, this is, and the second question is, are there winding families of symplectic forms? So winding family is just like a generalization of hyperkähler families. And the last question is actually for the modular space, it's defined as an infinite dimensional quotient because omega is infinite dimensional space. But can you describe this with the finite dimensional quotient, the quotient of symplectic cone by the geometric automorphism group? So that is, so the last question is because so it's true sort of for the complex moduli space for K3. So in some, so we asked this question in a symplectic setting. Okay, maybe I should go a little bit faster. And so I mean, here are some discussions about these questions. So there are some very partial results, okay, about these things. And I want to, okay, finally, in the section I mentioned the comparison between scalar forms and symplectic forms. So here I just introduced the notion of scalar type forms. That's, I first learned this from papers by Antov and Verbitsky. So it's just say this is just a symplectic form that's compatible with some complex structure. The knowns as C1, well, because we have the classification Kähler-Calabi surface as smooth four manifolds, so we know these four families, four manifold, the three manifolds together with the family, six manifolds have a Kähler type forms. So here actually, okay, this is what we know. For Kähler type forms, we know they form an open subset in the space with symplectic form. So this is like the notion, this is like stability of Kähler forms. And also we know cohomologous Kähler type forms are diffeomorphic. Okay, so what Donaldson really asked is, so we, like for K3, is every symplectic form diffeomorphic to a Kähler form? Okay, but when we restrict Kähler type form, we know more. So this is proved using some mixture of symplectic geometry and complex geometry. So for K3 T4, this is more or less due to Susan Tillman, Antov Verbitsky in the straight 10, and for Enrichs and the hyperelliptic surface. So I observed with Sheng Zhenling recently. Yeah. Okay. So now let's move the log version. For the log version, so it's a pair. It's actually given by a pair, a four manifold and together with a divisor. So this is, so I'll talk about series joint works with Mac, Jiemin, and Sheng Zhenling. So we actually know a lot more about the log version. So here, to define it, let me start with the notion of symplectic, connected symplectic divisor. Oh, okay, I will explain that in the next slide. So here, okay, here is, okay, I want to call such, okay, any connected symplectic divisor dual to C1, I want to call it symplectic anti-canonical divisor. Okay, so I forgot to change that. And when you have an anti-canonical divisor, then the pair X and D is called a symplectic log Calabi-Yau surface. The first observations are the complement of D has trivial C1 because D already, so all the C1 absorbed by D. And then also the pairing between C1 and omega is positive because D is a symplectic divisor. And important examples are toric, symplectic toric surfaces, because the toric boundary, the toric divisor, is a symplectic anti-canonical. Okay. This is just the first observations. And here I have the notion of symplectic divisors. It's just basically just normal crossing divisors. And one important condition is I want these divisors to can be made simultaneously pseudo-holomorphic. So particularly, I cannot have two symplectic surfaces with negative intersection. Okay. Also, okay. So, but for normal crossing divisors, you can always deform them to be to satisfy this condition. Particularly, you can deform them to be omega orthogonal. Omega orthogonal ones always satisfy this simultaneously pseudo-holomorphic condition. And so the point is, I mean, with this condition, I can study these symplectic divisors using pseudo-holomorphic curve theory. Okay, and then given given the general symplectic divisor, I can associate a homological type. This is just a set of order set of homology classes. Okay, and then there's further observations about symplectic Calabi-Yau surfaces. So first of all, by adjunction, we know the combinatorial type of D has to be either torus or cycle of spheres. If you allow D to be disconnected, it could be the union of two tori, but cannot be a union of a cycle of cycle divisor. That's the only new case for disconnected D. By result, Eiko Liu and Alton Owner also proved using cybervision theory. X for positive X, so positive just means this condition, the pairing positive. For positive X, omega X has to be either rational manifold or a rational root for manifold. And actually, you combine these two facts using that D has to be a torus or cycle of spheres. So a symplectic log Calabi-Yau surface is smoothly either rational or elliptic root. Okay, so it cannot be like genus 2 root or genus 3 root. Conversely, any positive rational / elliptic root surface has a symplectic anti-canonical divisor. So this is proved by symplectic inflation. So you start with a known case that where you have a symplectic anti-canonical divisor. You use symplectic inflation to propagate to arbitrary symplectic structures. So there's like a characterization of symplectic Calabi-Yau surface. It's just well, in terms of positive symplectic rational / elliptic root surface. Okay. So it's actually a bit surprising that, so we know anti-canonical divisors are either torus or cycle of spheres, but they only live in the rational manifold or elliptic root manifold. So the divisor itself has B plus equal to 0, 1, because the ambient manifold has B plus 1. A bit surprise to us is that actually any cycle of sphere with B plus equal to 1 must be a anti-canonical divisor away from any, so after blowing down away from the divisor. So this is interesting. So sort of, so you're given a rational manifold, you see a cycle of spheres, and if you blow down all the -1 spheres, then the cycle of spheres, if it has B plus equal to 1, then it's actually the represents C1. Okay. All right. The first result of another result about such divisors is so-called a Tori version. It's a Tori version of rigidity. It just says that if you have two anti-canonical divisors, if you have a integral isometry on H2, taking the class of the component, taking the class of matching the classes of the components, in addition to matching the class of the symplectic forms, then these two divisors actually are strictly symplectic deformation equivalent. And moreover, if they're both omega orthogonal, then they're symplectic morphic. Yeah. So anyway, this rigidity implies that there's a big hope to really understand such divisors, maybe enumerate them. There are also similars to the log Calabi-Yau surfaces in algebraic geometry. So such surfaces have been extensively studied by Luyenga, Friedman, Gross, Hacking, Q, and many others. So they studied them in the context of cusp singularities, single K3, moduli spaces, and the Tori theorems, the degeneration of K3 and mirror symmetry. There are many study about the counterpart in algebraic geometry. So here I just explain what I mean by strictly homological equivalence. It basically just saying, okay, after diffeomorphism, they're homotopic, and the strict deformation equivalence just mean, okay, so yeah, they're connected by families. Okay, so this is not just up to diffeomorphism, but here the strictness corresponding to here up to a symplectic morphism. not just absolute diffeomorphism. Okay. So anyway, this is another result about such log Calabi-Yau surfaces. The third result I want to mention is that, okay, here it's about the existence of almost toric vibrations. So here, an almost toric vibration roughly is just a symplectic four manifold. Oh, okay. This almost toric vibration of a symplectic four manifold is just a Lagrangian vibration with only nodal singularities and the elliptic singularities. I'm explain that elliptic singularity occur in the toric setting. So nodal singularities, they just nodal singularities. Okay. The B here is a two-dimensional stratified manifold, possibly with a boundary in the corner. So this is introduced by Margaret Symington. And so the possible smooth four manifold emitting such structures were classified by Symington and Conan Liang. Actually, Symington when observed that if the boundary is non-empty, then the inverse image of the boundary is a symplectic anti-canonical divisor. So there is a map from what I abbreviated ATF to symplectic LCY. So what we proved is that, okay, any symplectic anti-canonical divisor can be realized at the boundary divisor of some almost toric vibration. So we have sort of a map in the reverse direction. Slightly before our result, Engel and Friedman studied related question in algebra geometry. They construct such structure in the complement of the divisor. So we have this vibration fiber everywhere. Okay. And the corollary is that every positive symplectic rational elliptic root four manifold emits almost toric vibration. So, I mean, I mentioned that in the Calabi-Yau, symplectic Calabi-Yau setting, actually the one what we want to prove is existence of T2 vibration. Here in the log setting, we do always actually have a T2 vibration. Always have a T2 vibration. Okay, but it's actually moreover it's a Lagrangian T2 vibration. So it might be. I think the existence already is used to study almost toric vibration on K3 from Kulikov degenerations. I think it might be useful to understand the almost toric vibrations on all the manifolds in the list of Conan and Conan Liang and Symington. Okay, so lastly, okay, I want to talk about applying some results about Calabi-Yau surfaces to other type of surfaces. So just observe that this Calabi-Yau anti-canonical divisor satisfy this equality, right? So if you add D, the class of D to K omega, that's 0, or torsion, then you pair with omega, that's 0. So with Shengzhen Ning, we study the case, the negative case when the pairing is negative. They are sometimes the symplectic counterparts of the log Kodaira minus infinity surface in algebra geometry. And the first observation is that, okay, X is positive, X omega is positive. Okay, and another thing, okay, in the Calabi-Yau case, D is either torus or cycle of sphere. In this case, D is a tree of spheres. Okay, this is tree of sphere. Okay. The first result we obtained is that, okay, so assume D is connected, then we obtain a ruling, symplectic ruling in a complement of D, actually in a subset of complement D. So you remove a few symplectic surfaces, Si. Then you have a symplectic affine ruling. So affine means here, the S2 minus point is a disk, which is like a C. Yeah. So the algebraic geometry that exists in the affine ruling for log quadratic minus infinity surface is a classical result by Fujita, Miyanishi, Suji, and Russell. So they proved in the early 80s. I don't know, I have time, but the point is here, actually in one important, very difficult case, we need to use symplectic anti-canonical divisors. Okay, here in this relative setting, instead of one blow up, blow down, we have 4 types of blow up, blow down, according to the relation of the exceptional curve with the divisor D. We call like half toric, non-toric, toric, exterior. Okay. Here, the first important reduction is, okay, you can reduce the case either B2 is really small or quasi-minimal. So to define quasi-minimal, we need to look at the exceptional class, symplectic exceptional class with a minimal area. So here's one situation where we see some real symplectic geometry. We use the omega area, minimal omega area here, very essentially. And I think probably I'm not going to explain this, but you'll see Cyber-Witten anyway here in the. So I give you a couple of pictures here. So there, in a quasi-minimal case, we further divide into 2 cases. One case is like a comb-like. One case is like, okay, it's chain-like. And it is chain actually can be completed to a cycle sphere just by adding a minimal area symplectic sphere. So you see, in that case, the symplectic anti-canonical divisors are useful. Okay, so this is a one application. Another application is about weighted projective plane. So this of course can be defined holomorphically, but it also can be defined symplectically as a symplectic reduction. And so it has 3 singular points if you assume ABC a co-prime. And then you can take a resolution, symplectic minimal resolution. And I want to mention, Wei-Ming Chen showed the cohomologous symplectic forms on weighted CP2 actually diffeomorphic using orbifold Cyber-Witten theory. Orbifold and orbifold pseudo-homomorphic curve theory. So maybe I just, okay, this is, basically maybe just want to mention, okay, this is what we're through very recently. Basically, we have a characterization of a minimal resolution divisors of weighted projective planes. So maybe I will mention here. So the resolution divisors actually satisfy this negative pairing conditions. Okay. So it's but here the difference here, D is not connected. D has 3 branches, 3 strings. You have 3 singularities. So you have 3 strings of spheres. And the point of the theorem is, so if you use 3 strings in a rational manifold satisfy some condition, then we should show they must come from resolution weighted projective planes. And further prove Tourette type rigidity of such divisors. Okay, I stop here. Thank you.
Thank you for the nice talk. We have still several minutes for a discussion. Any questions, comments from the audience? Okay. Yeah.
Thank you for the nice talk. I'm not an expert in symplectic topology, but
there's expert there.
yeah, but actually I work in Cyber-Witten theory.
Oh.
And yeah, I'm curious about the toric vibration structure you mentioned on the symplectic RBL manifold. And I'm curious about what's the relation of such a vibration with the one of the Lefschetz vibration, which is more familiar to me.
Oh, these toric vibrations are certainly not Lefschetz because the fibers are actually homological trivial. For Lefschetz vibrations, the fiber is symplectic, so they represent non-trivial homology classes. But for K3, the story is different. For K3, there's a close relation between torus vibrations and the Lefschetz vibration. In fact, you have this hyperkähler trick rotation. You can turn a Lefschetz vibration, holomorphic vibration, to a Lagrangian vibration, and vice versa. Okay, but here the case the case I stated is for rational manifold, so B plus equal to 1. So any Lagrangian surfaces except Lagrangian spheres are homological trivial.
Okay, thank you. So furthermore, can we expect that we can also get restrictions on the Lefschetz vibration structure on Calabi-Yau symplectic form manifold? Like,
from that,
it's or something other.
Well, it's not clear to me, but I think there's related, but I don't see a clear implication.
Okay, thanks.
Okay. Maybe.
Okay, so let's thank speaks once again. Yeah. Oh, okay, where's the second speaker? Song? OK， 你把那个话筒给带起来。I move to the opposite. Maybe it's. Yeah. Get ready. Okay. So let's start. Second speaker, is Professor Sun Song from Zhejiang University. He's going to talk about gravitational instance and harmonic maps. So let's welcome.
Yeah, thank you. So I will talk about the gravitational instance and the harmonic maps. So this talk is based on joint work with Mingyang Li, who was my former student. He's now a postdoc at the Simon Center for Geometry and Physics at Stony Brook. This paper was posted last year. So we will be interested in studying this Riemannian Einstein matrix. So these are Riemannian matrix, complete Riemannian matrix, which satisfy the Einstein equation, the analog of the Einstein equation in the Riemannian setting. So this is a difficult PDE system. We're solving the metric, and the metric is the space itself is a variable. So this is in general very difficult, and there's no general method of creating solutions. It has deep connections to topology, algebraic geometry, and physics, and but we do have a lot of solutions, and these solutions they often they come by imposing special geometric structures. For example, if you work in the case of Kähler matrix, so you have the compatible complex structure, the structure of complex numbers, then this is a well-known theory of Kähler-Einstein matrix, and there's a well-established theory connecting this matrix to a complex algebraic geometry, and there are also connections to quaternions and octonions. This through the special holonomy in higher dimensions. The long-term program is to understand these metrics, the solutions to these equations. You want to construct solutions, and you want to classify solutions. So in low dimensions, in dimension 2 and 3, these have constant curvature. So as a PD is probably not very interesting. But in too high dimension, if the dimension is bigger than 5, there's we don't have many solutions, but we also do not have many obstructions. So we don't really understand what's the constraint imposed by this equation. So the most interesting case for us is the case of 4 dimensions. This is like a borderline case. It's not too flexible and it's not too rigid. So in this talk, we will be mainly interested in this gravitational instances. So these are just the name for a 4-dimensional complete Ricci flat matrix with quadratic curvature decay, which by general theory is equivalent to as a finite L2 norm on the curvature. So we will always assume the manifolds are oriented. So this will be convenient for our discussion later. So this terminology comes from Hawking, but mathematically, the interest is that this gives singularity models for 4-dimensional Einstein metrics, because these are complete metrics, Ricci flat metrics. If you just you can scale it, scale down it, and then most likely it will form singularity. And if you have a general 4-dimensional Einstein matrix forming singularity, if you rescale it, if your Einstein metrics have uniformly bounded energy, the L2 energy, then you will get these objects as bubbles. So this is a very beautiful subject. On one hand, we have many constructions of gravitational instance, and so a lot of come from physics, and then also there are many mathematical tools of constructing them. So it has rich geometry and analysis. So if you see the literature, there are many constructions, and then you wonder like whether you can actually classify them. So but to make it convenient for discussion, we will categorize this gravitational instance into 4 classes, type 1, 2, 3. So so even in a 4-dimensional case, gravitational instance has no Ricci curvature, no scalar curvature. So the only curvature not mentioned is the wire curvature, and because in 4 dimension the self-dual 2 forms, the bundle of 2 forms decomposes into the self-dual and non-anti-self-dual parts, and the wire curvature tensor acting on lambda 2 preserves this. So if you take the self-dual part, then you get the W plus this self-dual wire tensor. It can be viewed as a endomorphism of lambda plus. So it's a rank 3 bond. So at each point, a 3 by 3 matrix, and it's no trace. It's symmetric. So it has 3 possibilities. It has either 1 or 2, so 3 distinct eigenvalues. So when it has only 1 eigenvalue, then it's identically 0. And if generically it has 1, 2, 3 distinct eigenvalues, then we just say the G is of type 1, 2, 3. This is just for convenience, and this depends on the orientation. So for a given metric, for different orientation, it may be of different type. When you have fewer eigenvalues, you have more constraints on this tensor. So in the case of type 1, so W plus equals 0. This is the same as saying this matrix locally hyperkähler. So locally, so W plus is 0. So the curvature on lambda plus is identical 0. So that's a flat bundle. So locally, you can choose 3 parallel self-dual 2 forms, and that corresponds to 3 integrable compatible almost complex structures. So that's hyperkähler case, which is the same as saying the holonomy group of your metric locally is contained in SU2. So there are many examples. There are simple examples of top knot metric. So I'm not going to give the formula. It's an explicit metric. It was first derived by solving ODE. It's topologically, it lies, it's on the space R4, standard R4. It is not flat, and the volume growth rate is cubic. The flat metric has quartic volume growth. So in the end of this talk, I will give you a way of writing down the formula. But right now, just this is a new Ricci flat metric on R4. Was first, I think these are all physicists constructed them, and it was realized later by Claude Brun that actually, if you pick any compatible, almost complex structure, the underlying complex manifold can be identified with a standard C2. And you also have this metric on the cotangent bundle of S2, called Calabi-Iguchi-Hansen metric. It was constructed independently by Calabi and Iguchi-Hansen. Who did it first? So I agree with that. So that's, I think most often people just call it Iguchi-Hansen metric. I think because I'm a descendant of Calabi, I tend to put Calabi's name there. Anyway, but if you do Kähler geometries, Calabi's method works more generally for these bundles over Kähler manifold. So it's the so-called Calabi ansatz. This is also a metric solved by ODE. As you see, there's the cotangent bundle of S2. You can be there meets a symmetry of SU2. Cohomogeneity 1. So this metric is it is of quartic volume growth at infinity is asymptotic to a cone, and that cone is a quotient of R4 by Z2. So it's a cone over the three-dimensional projective space. And then there are many more, and the type 2 case is you have two distinct eigenvalues, and it's what I think it was first realized by Dzerzhinsky, that this is the same as saying that the metric is locally Hermitian, and it is not locally Kähler. So there's a complex integrable complex structure. So the metric is compatible, but the associated form is not closed. So, and then the interesting, so this, I mean, when you do, if you're familiar with Kähler geometry, when you move into a Hermitian setting, normally you would be complicated. But here, actually, there are natural metrics which are Hermitian here. So this is the remaining Kerr metric. So you take the Kerr metric in GR and you change T to IT. So this metric is a complete metric on the product of S2 times R2. And it's asymptotic, so I will describe it later. It's asymptotically flat in a suitable sense. And then you also have, if you take the top knot and the Calabi-Iguchi-Hansen, if you change the orientation, it turns out to be a type 2. So you see that type 1 and type 2 cases are very special. But interestingly, almost all known examples, I said there are many examples, but almost all of them are actually of this special type. So you expect most of the metrics of general type, but the one you can actually construct actually have these special structures. So except there is a explicit family of explicit solutions written down by Curie, Weinstein, and Yamada. This by explicit method. It's related to the what I will talk about later. Also use harmonic maps, but it's a further reduction of harmonic maps to geodesics. 12 years ago, I think if you talk about higher gravitational instance, so there are one thing I want to clarify is that in a lot of literature, when people talk about gravitational instance, they implicitly assume they are hyperkähler, in particular type 1. And so if you read the references, you have to be careful about that. But now I think recently we have seen a lot of progress in this understanding of type 1, type 2 gravitational instance. So they are essentially classified in type 1 case. So there is 4 families. These are refers to the asymptotical structures at infinity. It's LE, LF, LG, LH, LG star, LH star. Don't worry if it's just different types of asymptotics. For example, it could be a torus of dimension k times r to the 4 minus k. So that's the first 4 types, but then there are also special exotic types. And then a type 2 case was solved in the PhD dissertation of Ming Yang. And then it was based on previous work of Axtena Anderson and Bicart Gorduchon. So here they have 3 families, LE, ALF, and AF. So we were not, so if it's 3 years ago, I will just talk about this result. But now I will not explain the details of this, but just to say that this kind of results will rely on a few ingredients. First, we want to understand the infinity structure, the asymptotic structure of this space. This depends on the, so when you scale down this metric, normally you're not, if it has Euclidean volume growth, then you know it's LE. That's the old result of Bandu, Kasue, and Nakajima. But otherwise, you will see collapsing to lower dimensions, and this will rely on this collapsing theory of Chigov-Gromov, and also there's so when you scale down this space, then you have boundary curvature except at the one point, and the base point, the curvature will blow up. So you only have this boundary curvature collapsing away from a base point. But at the base point, there's a singularity. It has a curvature blow up, and it's collapsing. So there's no general geometric analytic method to control the structure of the singularities. There's no monotonicity formula, correct monotonicity formula for studying these kind of singularities. So what we realized that this singularity itself is controlled by the special geometric structure on the regular set. So we know that singularity is surrounded by regular points, right? And then on the regular points, they're collapsing from hyperkähler, for example, in the type 1 case, from the hyperkähler structure. So they actually gives to some affine structures at the on the regular set, and then you actually you don't really need to study the singularity itself. The singularity is controlled by the nearby structure. That's the to understand the asymptotics. And then once you know the asymptotics, you still want to classify the bulk side, what's inside, and that will depend on connection to the theory of complex algebraic surfaces. You want to choose the correct complex structure and compactify the space by adding certain divides at infinity. So this is along the line of Yao's conjecture, the compactification conjecture for general Calabi-Yau metrics. So in these settings, one can try to realize those. Okay, so that's all I want to say about this old development. So before we move on, let's just explain a little bit this one of these models. Sorry, a few of these models. So ALE model is just a quotient of R4 by a finite group gamma. find a subgroup of SO4, which acts freely on the 3 sphere. And the ALF model is given by a finite quotient of the top knot. And then, so this is the thing that we're most interested in as the AF beta. We call it asymptotic flat. So the notion of asymptotic flat is also not well defined in the literature, in mathematical literature. So in different contexts, they have different meanings. But here, for us, it's really just take a slab in R4, just R3 times the interval, and include the top and the bottom R3 by a rotation. So it's actually a rotation in the R2, in the plane R3 of angle 2 pi beta. When beta is 0, this is just R3 times S1, and that's the asymptotics for the Schwarzschild metric. So that's Schwarzschild is one belongs to the family of Kerr metrics. So the general Kerr metric will have this AF beta asymptotics. When beta is rational, this model at infinity is asymptotic to a 3-dimensional cone. So R3 quotient by certain by this rotation. But when beta is irrational, then this space at infinity has a 2-dimensional asymptotic cone, which is a half plane. So this is still the classification result of Ming-Yang in the type 2 case, so in the ALF and the AF cases. So so this double coverage to make sure that the space is globally Hermitian. So then actually there's only 4 families. There's a Riemannian Kerr, anti-top knot. I've already talked about that. And top bolt is top knot with a knot replaced by a bolt. So there's a CP1 inside this space. It's also a explicit construction using ODE. But then there was a surprising discovery by Chen Teo in 2011, which I think was overlooked a lot in geometry, at least to me. So it's some explicit metrics on CP2 removing a circle, but it's not easy. So this is their paper where it's a new AF gravitational instant, and they basically they want to investigate this kind of Riemannian analog of the black hole uniqueness conjecture, and they provide a counterexample to the conjecture, and then they found a completely explicit solution, and the solution is given by rational functions. It's quite mysterious. The method is using integrable system method. So it's very interesting. So this is our main result. So we basically we put this Chen Teo and Kerr metric in a general family of gravitational incidence with this asymptotics AF beta. So this is manifold is S2 times R2. You connect some a few CP2s and a few CP2 bars. P and Q, the difference is at most 1. So one thing is that the first, this beta has to be between 0 and 1, strictly between 0 and 1. So we cannot make beta equal 0. And then when P and Q equals 0, is S2 times R2. This boils down to Kerr matrix. When P equals 1, Q equals 0, this gives a Chen Teo matrix. And in other cases, these metrics are new. They are actually of type 3 for both orientations. This is the first step. If we want to understand general gravitational incidence, we need first to construct some examples. But we're still a long way from understanding systematically or classifying this matrix type 3. So these metrics are not, they do not have, because they're type 3, they do not have connections to complex geometry. So they have to be constructed from other methods. So our motivation is this black hole uniqueness conjecture. So in the Lorentz setting, as far as I understand, this is in the setting of stationary axis symmetric case, you have a reduction of the Einstein equation, a vacuum Einstein equation, to axis symmetric harmonic max from R3 into the hyperbolic plane. But interestingly, in the Riemannian setting, if we consider four-dimensional Ricci flat matrix, which is invariant under two-torus action and certain assumptions, then you can also be turned into axis symmetric harmonic maps from R3 into the hyperbolic plane. The mechanism is different, and often you will get a singularity behavior along certain rods, and the singularity behavior actually are different in the Lorentz and the Riemannian setting. Anyway, but I think the main problem, as I will explain, so now if you turn the equation into a harmonic map equation, and this is a negative curve target and flat source, so analytically, you see the possibility of understanding them. But then, and actually, you can actually solve this harmonic map equation. But then the point is that when you turn these harmonic maps into Riemannian matrix, then you will, in general, see conical singularities along a codimension 2 set. And these cone angles, they are not computable in general. It should be so that's the main difficulty. So if we want a smoother metric, then we have to show that these cone angles are all equal to 2 pi. So let's just explain briefly how do you do this reduction. So we consider a metric on just a product, a two-dimensional ball times T2, and then it's a G lower bar. That's just base metric on the base, and we consider the fiber metric. There's no mixed term. We assume there's no mixed term, and that's the manifestation of the integrability of the horizontal foliation. And then you have fiber metric, which is just a metric on T2. We want this to be invariant on the T2 action, so this becomes a map from the base to the symmetric space SL2 mod SO2. And then you can compute the Einstein-Hilbert functional. You get all these terms. You immediately see that there's this harmonic map energy density terms there. So you see that if you want to study the Lagrange equation of this Einstein-Hilbert functional, you will see the harmonic map. And here is the axis symmetric harmonic map. So so this, in general, this rho is the conformal factor it's a function on the base. But then if you, being Ricci-flat also requires that this rho can be turned into a isoformal coordinate by adding a conjugate z. So this rho is actually harmonic on B. So so you can take rho and z as coordinates, local coordinates, and conformal coordinates, and then you have to turn this rho into a rotation in R2, and then this phi becomes a map from R3 to this symmetric space, which is harmonic. And this conformal factor nu equal to nu, this nu actually can be determined by phi up to a constant. So then the equation Ricci-Flat equation really boils down to understanding this map phi, axisymmetric harmonic map. And globally, if we want to understand to put topology on it, then we will need a notion of a rod structure. So this is kind of an analog of the what's called de Azam polytope. If you study toric Kähler geometry or symplectic geometry, but here we are in the Riemannian context. So you have they have turning points, which is so the axisymmetric harmonic map will the singularity will be on the z-axis. Okay, rho equals 0. So there's a few points on the axis we call turning points, and we have a lattice in R2 and a rod vector for each rod, for each interval between these turning points. So that tells basically you want so generically your space is a T2 fibration. As you approach this interior of the rod, one of the circle shrinks, and that circle will correspond to this rod vector. And we put an asymptotic type, which normally is AELF or AF beta. And given this data, we will be able to actually construct a smooth four manifold just by taking this interior over the interior of the this is a half plane, rho z half plane. Take its T2 bundle, it's R2 more lambda bundle over it, and then you compactify according to which circle you wanted to vanish in which rod. So, and then this is given a rod structure. There's a unique axisymmetric harmonic map with given asymptotics at the turning points along the rods and at the singularity. I think if you do this harmonic map theory, then this is not very difficult. You have the negativity of the sectional curvature of the target is negative. And then once you get this unique solution phi, then you can choose nu, but this nu is only determined up to a constant, but you can adjust constant so that this singularity for the Ricci-Flat metric, you will only have singularities in the compact set. At infinity, there's no singularity. So this will have the correct asymptotics at infinity. And then at the interior for each rod, because one of the circle vanishes, the other circle does not vanish. So you take a circle over this rod and then you vanish on the two endpoints, you get a two sphere. So that will have cone angles in general, and it's given by this formula. So it's like understanding the interior value of a harmonic function with a given boundary. So of course we don't have explicit understanding of this. And then but I want just to mention that before you study this, then you want to say that actually this metric has a correct regularity along the rods. Like when you say it's conical, it has actually good regularity. So this is well studied in the Lorentzian setting. In the Riemannian setting, actually you can get a better regularity by using because this Ricci-Flat metric in the Riemannian setting is elliptic, so you can do elliptic geometric analysis. So now the difference is that in the Lorentzian setting, to prove this stationary axisymmetric black hole uniqueness, you want to say that if your rod is non-trivial, you don't get a solution. So you don't get a smooth solution. That means you always have a singularity. So the cone angles must appear, right? And then in the Riemannian setting, we actually we tried a different goal. We want to show that the cone angles can be eliminated. We can make them equal 2 pi for suitable choice of rod structures. So this is actually interesting. I mean, it's a very simple thing. If you have a continuous function on an interval 0 to 1, And if you do not have any understanding of this function, then you have two questions. Either you want to show this function is never zero, or you want this function has a zero. So the first question is much harder. The second question is easier because you can do you just need one value is positive, one value is negative using continuity. So it means that the Riemannian setting, in principle, if it works, then it actually is simpler. So here, for our construction, we just take this rod structure. I think you don't need to care about this formula. Let's just take this picture. So it's so this length of this rod, this is to be adjusted. But then for each rod, you go first horizontal and then vertical, and then this 45 degree, then vertical. I mean, so this is just it's not a very complicated thing to do. But if you do this, then you can read out this topology. And then I'll go, I mean, what we actually really proved is that you can choose that you can find the correct rod length so that the cone angles can be eliminated. So our proof is by existence. So we don't know what is this L, and we don't know whether it's unique, although we expect this L should be unique once beta is given. And in our proof, we assume that beta has to be strictly between 0 and 1. And actually one can prove, we proved that when beta goes to the boundary, then the gravitation has to split into the union of this known and this type 1, type 2 gravitational instance. So this idea is not complicated. So you have you would denote for each rod length, I denote the theta j to be its angle. So we have a map from this. This has a correct parameter. You have n parameters. You have n lengths. You have n angles. You want to choose a length so that this this map A and the image contains this point. And then we define a background metric A0, and then we just run a. You want to use degree argument. You want to show that this A can be connected to this A0 by avoiding this point on the boundary of a big cube by avoiding this interior point theta 0. And then if you want to do this, then we need to understand two things. Is when we pick a very big cube in the configuration space of the length, so it means that then we want to understand what happens when the length goes to infinity or length goes to 0. And that's so it's important to understand to obtain limiting information on the cone angles when the rod structure degenerates. So when the lengths go to 0 or go to infinity. So, and then analytically, you will need to do a bubbling analysis for harmonic maps. So this is done by comparing with a family of background maps obtained from green suitable rescaled model maps via the induction on scale. So it's important that we actually do this bubbling for harmonic maps. So we know that in the end we want to construct a gravitational instance. The space, but not all these bubbles. If you do the bubbles for harmonic maps and the bubbles for the gravitational instance, you will get differences. So the bubbles for harmonic maps, you get more information because there are bubbles which do not really correspond to gravitational instance. Because for in the side of a gravitational instance, you will see collapsing, and when the space is collapsing, you don't get rich matrix anymore. So it's important that we in this step, we deal with the harmonic maps instead of the Riemannian matrix. But this only gives you a abstract thing, like when you form singularity, when this degenerates, you get some understanding of the of these harmonic maps, but these harmonic maps into a simpler harmonic maps, but it does not automatically yield information on the behavior of cone angles. So there actually, this is an interesting thing. So there's a bad news is that in some cases, so you have n parameters, you have n equations you want to solve, you want to find a particular solution, right? But then in some cases that this angles it does not vary at all when we vary rod length. So this map could be a constant map. So if you just have a constant map, then there's no way you can adjust it unless you already know it contains the image you want. And this is actually the case in the example of Calabi and Gucci-Hansen. This is a hyperkähler case. But there's also good news is that in some other cases, the cone angle can actually vary in the way that we want. So this is the type 2 case. When you consider the Kerr matrix on S2 times R2, if you fix beta, then we have a family of metrics with cone angles. So when you view the rod length go to 0, then cone angle actually go to infinity. And as the rod length go to infinity, the cone angle goes to 2 pi beta. So if beta is smaller than 1, you see that there must be a place where the cone angle is exactly equal to 2 pi. So there's a question related to what Chen-Thiel disproved, that is remaining black hole uniqueness. So so the Chen-Thiel metric is also have this AF beta asymptotics. So if you work in this AF beta asymptotics, for example, the Kerr space, they do not have uniqueness. The space is not determined by the end only. But all these examples of Chen-Thiel and us, we have to ask beta to be bigger than 0. So what if when AF 0, when beta equals 0, we believe that this might be the right conjecture to formulate. And for general, if you want to have a uniqueness in a general case, a general beta, we probably want to fix the underlying space xn. So last 3 minutes. So how do we see these metrics are not are type 3? And actually, this is related to we actually have understanding of these harmonic maps in terms of its degree. So we have a rod structure, then we can actually compute its degree. It's just how this rod varies. And so if you have a rod like here, V0, V1, V1, this is a curve. You want to go from V0 and V1. So each time, if we only allow counterclockwise rotation by angle less than pi, then this first curve, you just rotate once in RP1. So that degree is 1. For Chen-Thiel, degree is also 1. But then if you have more rods, then degree gets higher. So this is a topological invariant. And we proved that you can tell this type from the degree. So if degree is 0, then type is 1, if and only if, and type 2, if and only degree equals 1. So type 3, if and only degree is bigger than 1, that's why the new examples all have type 3. And in both type 1 and type 2 cases, actually phi has an explicit form in terms of axisymmetric harmonic functions. So this actually is an interesting consequence for harmonic maps, for axisymmetric harmonic maps. So this result is independent of this integrality, this lattice. We don't need this lattice. So you can form a statement for just for harmonic maps. So in these 2 cases, when the degree is small, the harmonic maps can be turned into harmonic functions, and this harmonic function can have explicit formula. So in type 1 case, this harmonic map is constructed by Gibbons-Hawking ansatz. So if we have a positive harmonic function, which is axisymmetric in R3, and if you then that f will be its harmonic conjugate, then the harmonic map into the right plane or the upper half planes, V and F, two components. V is always positive. And then this is just this is a standard Gibbons-Hawking ansatz. What you get is hyperkähler. So if you take a simple V's, you will get this the matrix I mentioned in the beginning. So you can get very explicit formula for these spaces. And the type 2 case, you can also be turned into harmonic functions, but it's much more delicate. So this is called the Lebrun-Todd ansatz. So if you're given an axisymmetric harmonic function U, this time you let H to be the harmonic conjugate of U. So you see here U is not necessarily positive. And then the harmonic map is given by this pair V and F coming from U and H. And then if you do the top knot and change the orientation, it's type 2, and it corresponds to this complicated thing. And then a question one can ask is that if you have a degree bigger than 1 axisymmetric harmonic map, can we find explicit formula? So it's known that this harmonic maps they correspond to integrable systems, and they have Lux pairs, and they have Belinsky-Zakharov formula. I mean, that's how Chen Thiel get their solution. But it will be interesting also to get these new solutions by this formula, by explicit formula using integrable system method. Okay, I think that's all I want to say. Thank you.
Okay, thank you. Questions?
So I have a general question. So you mentioned for the the case of closed manifold. So there's like a relation between stability and existence of Einstein matrix, right? So I wonder in the case of gravitational instants, are any notions of stability and also like classifications in terms of stability?
Yeah, it's a good question. So first, that's this stability thing that only apparently it's only appears exists in the Kähler setting. So that means maybe for gravitational instance, you're probably only interested in the type 1 case, the hyperkähler case. So that's the general question about. So you can view this as if you fix a complex structure, you can view this as a Calabi-Yau metric on the open Calabi-Yau metric. So we have attempts to understand this in terms of stability of this non-compact algebraic manifold. But I think this I mean, I have some conjectures in some suitable settings, but I think it's technically still very difficult to go.
Any other question?
Question here. Do you expect these metrics to appear as bubbles, and like in what situation? Like,
yeah, that's
what
good.
manifolds do you?
It's a good question. So there's no reason that it does not appear as bubbles for.
Do you have any idea what the manifold should be?
Yeah, the point is, if I talk about this Ricci-Flat non-compact complete metric, right? If you go to a compact Einstein full manifolds, there's also not so many examples actually known. So you think, I mean, we have this scalar Einstein matrix, we have the Hermitian Einstein matrix, Chen-de-Bruyn-Weber. But then in the negative Einstein case, there are some construction by Dan Finney and stuff. There are some construction, but still we do not really, but lack of a systematic construction in that setting. I expect for example, this you can there's a similar question you can try to understand the toric Einstein matrix with positive Ricci curvature in 4 dimensions, compact, and then you can also form similar questions. And there, if you can find examples there, they might be related to this bubbles here. So it's
maybe this toric is just asymptotic, like sort of.
Say again.
Like you expect the Einstein metrics to be toric if they were to form bubbles? It could just be an asymptotic.
No, but I'm saying that you can try. I mean, there also you can try to work out the toric Einstein metric first. So
there's this a big open conjecture about like Ricci flat metrics with generic holonomy. On do you think this is? I don't know if there's any chance of.
Yeah. So the motivation of this and. I mean, actually this project, the original motivation was trying to, I mean, so you have the compact case, you have this question of Ricci flat metric with generic holonomy, but I think holonomy is not the correct thing. Just Ricci flat metric, type 3 Ricci flat metric, let's say. Okay, I think this in terms of the type is more natural. And there's also a related question for in the non-compact case, that's in the ALE setting, that's the Bandu-Kasui-Nakajima conjecture. So that's also difficult. But then it turns out that in this AF beta setting, you can actually construct new metrics. For example, in the ALE case, I think that would be an easier question to study than the compact case. But even that is not known. I have spent a lot of time on this, but I don't want to.
One more question. Maybe this is is the type, like if you have bubbles bubbling up, is the type preserved? Like type 1 only bubbles up, type 1, type 2?
No, you can see there's like a matrix can degenerate, right? Type 2 can become type 1, right? So
yeah, but does it go the other way?
No, this is just this is simple continuity of eigenvalues when matrix comparison. So yeah, but definitely in for example, right. So when we say this this splitting, this can also be seen as a bubbling phenomenon. So when this beta tends to 0, 1, so these are type 1, type 2 metrics. So we should, I mean, I tend to think of this this gravitational instant as kind of nonlinear superposition of this type 1, type 2 matrix. It's kind of as beta is degenerated, this you can think of this as gluing of this.
Okay, thank you.
Okay, for the time consideration, let's stop here and let's thank Song once again.
Thank you.
So our third talk will resume, I guess should be 3:45. So we still have several minutes to take a break.
Hello, Professor Carlos. Can you hear us?
Hello.
Yeah.
Carlos, can you hear me?
Hello. Yeah. Hello.
I'm not sure you can see me.
Who is this? Is this?
Wait.
I see the room, but I only see it small, really.
Yeah. 现在是哪？ Yeah， 这个吗？ Okay. Yeah, just sit. Yeah, you can see me now, I guess.
I guess so, but it's very small. But yeah, hello.
Okay. This is my essential image.
Yeah, exactly.
I'm looking forward to your talk. Yeah, I can
Yeah, I think.
say, I think. Yeah. So yeah, it's higher homotopy group, right? It's about
Higher homotopy groups. Yeah, yeah.
Great. we have a 1 minute. 1 minute. Okay. Carlos, are you ready?
Yeah, I'm ready. I'm ready.
Okay. So our third speaker is Professor Carl Simpson. He is going to talk about higher local monodromy using the logarithmic theorem stack. So let's welcome.
Okay, thank you very much for the hello.
Yeah.
Can I start? Hi, thank you very much for the invitation. It's a great pleasure. I'm sorry I was not able to travel sometime in the future. So I'd like to talk about higher local monodromy using the logarithmic theorem stack, and I'll be motivating this a little bit with secondary Kadir-Spencer classes also, which I looked at a while ago. And also, let me just introduce. Can you guys? Did this cut off the top of the slide for some reason? No, I'm not sure. Anyway, is it okay?
It's okay.
Okay, good. So suppose we have a smooth projective morphism of smooth complex varieties. And then there's a discriminant locus in the base where the map is not smooth. Oh, sorry. Erase this word smooth. Generically smooth. Suppose F is generically smooth. I'm sorry. Suppose F is generically smooth, and then we have a divisor in the base where it's not smooth. Okay. We'd like to study the phenomenon of degeneration. So how does the topology of the fiber behave as we have points approaching the divisor? Okay. In the classical setting is when S is a curve and D is a finite set of points. And so those are points where the fibers are singular. And if we localize near one of those points, we can just look at a small disk in the base, and the singular point is at the origin. So if we have a point, a nearby point, which is not at the origin, then the fiber is smooth, and we have a monodromy transformation, which happens when you go around when the point eta goes around the origin. And this is actually a C-infinity transformation of the fiber, which is well defined up to isotopy. And so typically we look at the action of this monodromy transformation on the cohomology of the fiber. And so of course, this has been studied an incredible amount. One of the things I'll just mention is the Clemens-Schmidt exact sequence relating the monodromy action on the cohomology of the fiber and the cohomology of the central fiber. And so for the Clemens-Schmidt exact sequence, we assume that the map F is semi-stable. So it means that the central fiber is a reduced normal crossings divisor. And then the exact sequence is written like this. We don't need to know this for the rest of the talk, but just to show this. So here in particular, we have the logarithm of the monodromy operator. And so in the semi-stable case, the monodromy operator is unipotent on the cohomology, and its logarithm is a nilpotent operator. This nilpotent operator gives rise to a nilpotent operator weight filtration, Deligne weight filtration, which is part of a limiting mixed Hodge structure, and this becomes a sequence of mixed Hodge structures. This is sort of a main part of the theorem, really. So in this to get this exact sequence, one of the key notions is the notion of variation of Hodge structure. And we can just recall, I won't give the definition, but you guys know the definition, I think. But it relates the Gauss-Manin connection on the relative cohomology, the Hodge filtration, the Betty relative cohomology, and the Hodge metrics on the fibers, which vary. Okay, so now now I'd like to comment on because this is one of the topics of the conference, the Uhlenbeck-Yau theorem, the Narasimhan-Seshadri-Donaldson Uhlenbeck-Yau theorem, how that sort of modified our vision of the situation. Cohomology comes in several flavors for algebraic varieties. We have the Betty cohomology, which is just the usual cohomology, singular cohomology of the underlying topological space. But we also have a Durham cohomology, which in the case of an algebraic variety, it has an expression in algebraic geometry, which is algebraic Durham cohomology, and also Dolbeau cohomology. And the Hodge theorem tells you the isomorphism between Durham, Betty, and Dolbeau. Now, the Narasimhan-Seshadri-Donaldson Uhlenbeck-Yau theorem gave an expression for the non-abelian cohomology with coefficients in the unitary group, the non-abelian H1, which is to say the moduli space of representations, in terms of polystable vector bundles with vanishing Chern classes. And so the point here is that I like to make is that we can view this statement, the statement relating the space of local systems, that's a sort of a Betty cohomology, with the space of polystable vector bundles, that's a Dolbeau cohomology. So the vector bundle description we can think of as a Dolbeau version of non-abelian cohomology. And then Hitchin defined the notion of Higgs bundle, and along with that went the Donaldson-Corlett theorem on the existence of harmonic metrics for local systems. And then it became possible to extend the correspondence from the unitary group or from compact groups like the unitary group to non-compact groups such as GLN-C, and more generally any H1XG for a real or complex algebraic group. Okay. And then we get a whole package of structures for this non-abelian cohomology, which includes all the stuff that you have. You can make analogs of pretty much all the stuff that you have for usual Hodge theory, including Durham cohomology, Hodge filtration, harmonic metrics. The weight one non-abelian Hodge structure corresponds in a pretty close way to the hyperkähler structure that Hitchin constructed on the moduli space and to the associated twistor space. Okay. And then now it's natural to look for analogs of the Griffith-Schmidt, Kotani-Kaplan-Schmidt, Kashiwara-Kawai theory of degenerations of period maps, which is to say the stuff that led to for example, to the Clemens-Schmidt exact sequence, among other things. Unfortunately, this is not all that easy, and in fact, very difficult. So the study of degenerations for these moduli spaces in the non-abelian Hodge theory is a very difficult question. And we can ask for a non-abelian Clemens-Schmidt exact sequence. That was, I think, if I remember correctly, really Ludmila Katsarkov who first said, let's try to look at this. Anyway, we just spent a long time discussing with Ludmila and with Tony Pantev about the question. We didn't make a ton of progress in the sense of getting the theory for the H1 non-abelian H1 moduli spaces because it's very difficult. But it did lead to our paper on non-abelian mixed Hodge structures, and that was the first attempt to define a notion of variation of non-abelian mixed Hodge structure. That worked better as in the case which we'll be treating today, in fact, which is the case of rational homotopy theory for higher homotopy. Formalizing a complete generalization of the degeneration theory into the non-abelian Hodge situation seems to me to be far away at this point. But I should say that, but I haven't written down the names, but there have been several works going in this direction. So let me not say that nobody has done that. So some people have worked on this question, Richard Wentworth among others, but many other people also. However, I don't think we can say that there's any kind of complete answer to the question. Okay, so now what I'd like to look at today is a somewhat different but very related direction, where instead of looking at the non-abelian H1, now let's assume that the fibers are simply connected, so there's no non-abelian H1, and look instead at the rational homotopy types of the fibers. So we'll think of the rational homotopy type as a kind of a higher non-abelian cohomology space, or the homology space in that case. And the reason why one of the reasons why it makes why it's a good idea, you might say now, to look at this question is because there's been recent progress by a number of people, starting with Dan Abramovich and Kale Karu, and then including Wlodarczyk, and then Adipasito, Liu, and Temkin, to prove the semi-stable reduction theorem in its full generality, which is to say, when we have a higher dimensional family over a higher dimensional base. The cases before that, two cases were, I mean, of course, Mumford, I think, was the origin of the semi-stable reduction theorem for families over a curve, over a one-dimensional base. Higher dimension, I guess, curves of families of curves over a curve. Then we had the higher dimensional fibers over a one-dimensional base, and we also had a semi-stable reduction for families of curves over higher dimensional base. But up until this recent work, semi-recent in 2018 maybe, it was not known how to do semi-stable reduction for families of higher dimensional varieties over parameterized by a higher dimensional base. But now we know how to do that. So now that we can do that, then it makes sense to say, okay, let's look at what this means for the Hodge theory of degenerations. So let's consider a morphism between smooth varieties, generically smooth morphism between smooth varieties, which is a semi-stable map. This implies in particular that the inverse image of the discriminant divisor, which I'll call that Q if you like, it implies that that's a reduced normal crossings divisor. But the condition of semi-stability is actually stronger than that. It has to do with which coordinate functions occur in the monomials that define the map, which basically is designed to make it have lots of nice properties. Now, we'd like to look at the homotopy types of the fibers. So we can try to define a Durham homotopy type. You'll see how to do this in a little while. We can try to define a Durham homotopy type of the fiber, and then we get a family of homotopy types over depending on the point S of the base. And this should really be thought of as a higher stack, as an n stack or an infinity stack. And it has a Gauss-Manin connection, which is just the analog of the usual Gauss-Manin connection. But it was first looked at by Navarro-Asnau in the case of rational homotopy theory. But it turns out that if you try to write this down in terms of rational homotopy theory using the typical expression in one of various expressions in terms of differential forms and so on, it's not so easy to actually write down what it means, the higher Gauss-Manin connection. But the formalism we'll adopt here actually works pretty well and gives you it doesn't give you a way of calculating it, but it gives you a way of defining it almost for free. We also get a non-abelian Hodge filtration, although that's not going to be, we don't need that for today. But there's a non-abelian Hodge filtration in the quote associated graded, which is to say the fiber over the 0 point in the family over A1 in the Riesz space, is the family of Dolbeau homotopy types of the fibers. And you have a Kadeira-Spencer map on non-abelian cohomology over the dual, which is the homotopy types, which gives you an action of the tangent space on the Dolbeau homotopy type of the fiber. And this includes the usual actions of the Kadeira-Spencer map on the cohomology or homotopy groups of the fibers. But this was something I did some time ago. There's can be cases where the action is trivial. Those Kadeira-Spencer maps are trivial on the cohomology. And then you can get secondary Kadeira-Spencer classes corresponding to the higher homotopy coherence of the action. And what I'd like to talk about today is that a similar phenomenon occurs for the residue of the logarithmic Gauss-Manin connection in the case of a singular semi-stable family. So let's recall we're given I just made this mistake again. Generically smooth, just erase the word smooth. A projective morphism of smooth complex varieties. I'm sorry about that. Such that the fibers are simply connected. And then we can define the Durham formal groupoid. Of course, over a general point of the base, it is going to be smooth, okay? So we can define the Durham formal groupoid, which is the group object. So this is the theory of group formal groupoids, which is underlying crystalline cohomology, and which I learned about from Berthelot's lecture notes in math book. We can define the Durham formal groupoid, which is it's a groupoid object in the category of formal schemes, and the object is just S, and the morphism object is the formal completion of the diagonal. So then we should picture this as being a way of joining together nearby points of S, infinitesimally nearby points of S, using little links, which are those are given by the morphism object of the groupoid. And since it's a category object in the category of formal schemes, and if a formal scheme will represent a sheaf on the big side of schemes, let's say affine schemes, say finite type maybe, then if we have a groupoid object in that category, then that groupoid object will itself represent a fibration of categories, which we can take the associated stack. So this represents a stack, which we'll call the de Rham stack. And in this case, it has you can notice it has a simplified form, which is the y valued points of the de Rham stack are equal to the y reduced valued points of S. So that's just kind of, I mean, I'm not sure it's all that useful really, but sort of a fun formula that allows you to define the de Rham stack in a very simple way. This can be used to define the de Rham stack. Maybe more useful for calculations is that this stack also the formal category, and this was explained in Berthelot's book really. The formal category corresponds to a Lie algebroid structure, or what is sometimes known as a Lie-Reinhardt algebra on the tangent bundle. And we have a morphism of stacks from S into S de Rham, and the morphism object of the formal category, the formal groupoid, is just the fiber product S crossover S de Rham S. Now we can do the same thing upstairs on X. Remember, we have our morphism. We have a morphism from X de Rham to S de Rham. Okay. Then we get the relative de Rham stack, whose fiber over any point is the de Rham stack of the fiber. Maybe I should say that to do this, it's actually probably better to look at the points where F is actually smooth. We're going to modify this later for the non-smooth points. Now, what is the de Rham stack? What's the meaning of the de Rham stack? Well, the point is that if we would like to look at bundles, or really anything, over the de Rham stack, it's the same thing as a bundle over S, because we can pull back together with a flat connection. So on S, an object over S de Rham, I mean, there's a map from S to S de Rham. So S de Rham is lower than S, okay? It's underneath S. And if we an object downstairs is the same as an object upstairs together with descent data for going down, okay? The descent data is the notion of a flat connection, really. That again was in, I mean, this is really due to Grothendieck in the D's Exposé monograph. But then it was adapted to crystalline cohomology and characteristic P in a number of works, including Berthelot's book. Arthur Ogus also had a book about that. Now, the stacky viewpoint extends naturally to higher homotopy by considering higher stacks over S de Rham. And that's the way to, that's like, you might say, the natural way to look at the Gauss-Manin connection on the rational homotopy type. So we can get relative homotopy and cohomology invariants, which are usual de Rham cohomology and de Rham homotopy type of the fiber. And these come from relative invariants for X de Rham over S de Rham. And that's how you can define the Gauss-Manin connection on the family of homotopy types. This gives you the higher homotopy coherence, sort of all packaged into one package. And you get the Gauss-Manin connection on the rational homotopy types as it was first investigated by Navarro-Asnau. Okay. Now, we can also take a deformation to the normal cone of the de Rham formal groupoids, in other words, the morphism objects for the formal groupoids, and we'll get Dolbeau formal groupoids. And these are associated to Lie algebroids, again, which is, again, sort of a deformation of the de Rham Lie algebroid, but whose underlying bundle is, again, the tangent bundle, but where the Lie algebroid structure is trivial, namely the bracket is 0 and there's the action of the functions is 0. The anchor map is 0. So then the Dolbeau formal groupoid is just a commutative formal groupoid whose morphism object is just the completion of the tangent bundle along the 0 section, and that's viewed at mapping to X cross X as, or S cross S, whichever one, as lying over the diagonal inside S cross X. And the picture of this is that these infinitesimal links between nearby points get squished together and become little infinitesimal loops based at each point. And then, so an action of the Dolbeau formal groupoid something is going to be really a Higgs field, basically. Then we get a relative version in the same way, and we can define a relative Dolbeau homotopy type. And then the cohomology and the homotopy types relative to S have actions of the since they have a descent data down to the Dolbeau formal groupoid, the formal to the Dolbeau stack, that means we have actions of the completed tangent bundle, or which is to say infinitesimal actions of the tangent bundle. And this is exactly the Higgs field. So this is the Kadeira-Spencer map. And in particular, you can define, if you like, the Kadeira-Spencer map on cohomology, and you can calculate it comes out to the same thing. So the usual Kadeira-Spencer map on cohomology is just given by doing what I said here. To look at the cohomology of the fibers in the sense of the, did I write this? Sorry. Well, in the sense of the map X Dolbeau to S Dolbeau, and then the cohomology of the fibers lies over S Dolbeau, which is to say it's something over S together with the action of the tangent bundle. That's really the Higgs field. And so, but now what I'd like to point out, this is for the talk today, is that since the tangent bundle, in this case, the Dolbeau case is an abelian group object, then we actually get secondary invariance as soon as that abelian group has rank more than a 1, then you can get secondary cohomology invariance. And there's if we say, okay, let's look for actions of an abelian group object, there's really two ways to get those. One of them is what I was saying before about the Dolbeau stack with the Kadeira-Spencer classes. Every point has an abelian group gerbe, so you have a Higgs field, and you get if you do it on homotopy types, the homotopy coherence property is going to give you a secondary Kadeira-Spencer classes. Then the topic for today is that we can also look at the Durham stack with logarithmic singularities along the divisor. And in that case, the part of the Durham part of the stack does not give you an action of an abelian group. It's not acting on anything because the links go from one point to another. But as you go if you go to a point of the divisor, then those links become shrink to 0. And on the point of the divisor, you have what you would say the residue, which is the action of a formally completed commutative group scheme located over the origin in the Durham stack. So that second thing is going to be the topic which we'll be discussing in a minute. But let me just review what we can say about secondary Kadeira-Spencer classes as motivation. So as I said, you have the Higgs field, the action of the tangent space on the Dolbeau cohomology of the fibers is the usual Higgs field. That could be trivial. In that case, if it's trivial, you get a secondary class, which we'll call secondary Kadeira-Spencer Higgs fields. So what I said so far is to look at the full Dolbeau cohomology type, but you could also just look at non-abelian cohomology, and this is what I used to calculate this in some example, which is to say, just look at non-abelian cohomology with coefficients in the schematic two-sphere. Schematic two-sphere is just a simple non-abelian homotopy type, which has two stages in the Postnikov tower, degree 2 and degree 3. And the Postnikov invariant is a map from H4 of GA2 into O, which is GA. O is the structure sheaf is the sheaf represented by the additive group scheme. So this is the class in H4 is going to be the class classifying the Postnikov tower of the two-sphere. And you could do an explicit example. So if you take a smooth projective surface with H20 different from 0, then let's let X be obtained by blowing up the diagonal in S cross S, or Z cross Z or S cross S, and look at the second projection. And then if you choose carefully a class here, where M and N are possibly complex numbers, which with the property that the class eta cup eta is 0 in H4, then you're going to get a map to the two-sphere. And you get a secondary Kadeira-Spencer class for this. And you can calculate that this secondary Kadeira-Spencer class is exactly the map which tells you wedge 2 of the tangent bundle into H2XO, whose Poincare dual is the evaluation map. And so this will be non-zero if H0KX is non-zero. So you can get a case where there's a non-zero secondary class in this way. Whereas the primary class, if you blow up a point in a surface and you move the point around, all the Hodge invariants, all the cohomology invariants, Hodge invariants, variation of Hodge structure and everything, those are all constant. Okay, so the secondary class gives you information which can allow to sort of see in a secondary way how the point moves around. But it's not something that depends on the tangent bundle. It's something that depends on the wedge 2 of the tangent bundle. And so the idea is that you could have the same type of thing, although I have to say I don't have an example where the Kadeyer-Spencer thing is well, I don't have an example where the primary residue actions on the cohomology are trivial, but you have a secondary residue, but you could imagine that example, and that's what we'd like to do today. Let me just say that this secondary Kadeyer-Spencer map is going to be the Kadeyer-Spencer term in the variation of non-abelian mixed Hodge structure, which was the subject of our article a while ago with Katsukov and Pantev. In this article, we looked a lot about the weight filtration and purity properties, at least as a first approach. I think that it's safe to say that needs further exploration in the current state of things. Okay, so now let's turn to what we'd like to do here, which is the case of logarithmic Durham-Gauss-Manin connection for degenerating families. Okay, so suppose we have a disk and its divisor. So let's take the case of a curve now again. Suppose we have a disk and its divisor, and suppose we have a vector bundle with logarithmic connection over S. Then you get a residue, which is the residue of the connection is an endomorphism. And if we assume that the residue of the connection is nilpotent, then the monodromy is unipotent, the monodromy of this vector bundle with logarithmic connection. The monodromy is unipotent, and the n is the log of the monodromy. That brings us back to the picture that we had for the Clemens-Schmidt exact sequence. So what we can do in this case is, now I'm just recalling completely classical, from decades and decades ago, completely classical considerations about logarithmic connections. But it's an interest. I think it's interesting to recall this nonetheless, because once you're given this vector, right? So what we said here is if you have a vector bundle with logarithmic connection, then we get a vector space, the fiber V0 over the origin, and a nilpotent endomorphism. But on the other hand, if we have just a vector space and a nilpotent endomorphism, then we can create a model of this logarithmic connection, which is to say we take this vector space tensor OS and we define the connection by d plus n times dz over z. Okay, so that gives us a vector bundle with logarithmic connection. Then the interesting point is that this model connection is isomorphic to the original one. So the data of V together with a nilpotent residue logarithmic connection is the same as the data of just a vector space. I mean, that's over a disk, of course. The same as just a vector space with a nilpotent endomorphism. And you can actually turn this into, for example, you have on the Tanakian category of vector spaces with unipotent monodromy transformation. You have an additional fiber functor, which is take the Deligne canonical extension and take the fiber over 0. So that's this V0 thing. That's like a different fiber functor, which is not an actual point on the circle, right? So if you have a local system over the circle with unipotent monodromy, that Tanakian category has a different fiber functor, which is this V0 thing. So that's I think an interesting philosophical thing to think about. You can also write this down in this way, which let me just skip that. And in higher dimensions, also, sorry about the spelling mistakes here. In higher dimensions, you can just do the same thing. So suppose you have a K-tuple of commuting nilpotent endomorphisms, then you can create a model bundle in this way. That will, if they commute, that will be a flat connection. And any logarithmic connection on the disk, on the polydisk minus the standard divisor with unipotent monodromy is canonically isomorphic to the, well, maybe you shouldn't say canonical. It's isomorphic in any case to the model connection. Okay, and let's just remember that this is really the first step in the classical nilpotent orbit and SL2 orbit theorems for variations of Hodge structure, is to do this unwinding of the unipotent monodromy transformation. And of course, that was also very present in Deligne's lecture notes on regular singularities. Okay, so we get the property that logarithmic connections with nilpotent residues satisfy strictness, which is to say, any morphism, if you have two different logarithmic connections with nilpotent residues and you have a morphism of logarithmic connections between them, then that morphism is strict at the origin. Of course, it's strict everywhere else because it's Durand, but also at the origin, it's also strict, okay? And we can turn this into another preliminary observation, which we looked at in a paper that I wrote with Jaya Iyer some time ago, which is that suppose you have a perfect complex with logarithmic connection in the higher sense, with respect to a normal crossings divisor, and suppose that the residues act on the fibers of the perfect complex nilpotently, which is to say, for every point, the action of the residue on the cohomology spaces of the fiber of this perfect complex are nilpotent. Then V actually splits as a direct sum of locally free sheaves locally on the base, which is to say, again, the perfect complex actually has to be just a direct sum of bundles, which is to say there's no jumping of the cohomology dimensions. The basic reason is that if you had jumping of the cohomology dimensions, that forces the residue of the connection to have eigenvalues that differ by an integer. And if the residues are nilpotent, then all the eigenvalues are 0. And so they can't differ by an integer. And that's kind of a very similar statement to this strictness statement. Pretty much the same. Okay, now we can also define a logarithmic Durand formal groupoid. So suppose we have a smooth complex variety with normal crossings divisor. Then we can define S Durand log D. And one way of saying this is take the formal groupoid whose associated Lie algebroid is the sheaf of tangent vectors that are tangent to the divisor. Then we get the corresponding logarithmic Durand stack, which is the stack associated to this formal groupoid. There was a recent preprint by Michael Bars about logarithmic Durand stacks that brought this up. And in some way, if you try to draw this picture of the links, what I was saying before, the Durand picture has little links joining together nearby points in the variety. But at the origin, those links shrink down to 0 and become just loops at the origin. And that loop in this case is the residue. Somewhat contrary, it's not actually an action of the tangent bundle. It's an action of the logarithmic tangent bundle at the origin, and that has a canonical basis contrary to the tangent bundle. So really, the action of the residue at the origin is actually a well-defined quantity. And again, we can do the same thing as before. The morphism object of the formal groupoid is the fiber product for this descent map along the Durand formal groupoid. And we can also describe what the Lie algebroid actually looks like along each stratum of the stratification of the divisor. It's going to be an extension of the Durand formal groupoid of the divisor strata by some constant space, which is the space of residues. So this R thing is it's the space on which the residues map is going to be defined. And so R is just a trivial bundle, which has trivial Lie algebra structure, of rank equal to the codimension of the stratum in the divisor. And we can get a relative version the same way as before. Then we'd like to use these logarithmic Durand stacks to define a relative logarithmic homotopy type. Now, to be more precise here, I was kind of vague a little about this at the start. We can use Bertrand Tohen's theory of affine stacks and schematic homotopy types. For our purposes, we don't really need the full theory of schematic homotopy types, which was the second part of the paper on Tohen's paper on affine stacks. The first part of the paper was on what called affine stacks, champs affines. And those are kind of good enough to talk about the homotopy types of simply connected things. So these schematic homotopy types are going to be n stacks on this big site of affine C schemes with a topology whose restriction with some restrictions on the homotopy group sheaves. to talk about the homotopy group sheaves, well, let's notice that if everything is one connected, then we don't need to worry about the base point section. And we're going to ask that the homotopy group sheaves be of this form, some power of the structure sheaves. In other words, they're just going to be direct sums of the unipotent group GA. And schematic homotopy types with those restrictions on the homotopy group sheaves are what Tohen calls affine stacks. Okay, so we can just use that theory. Now, in the relative situation, so the characterization of so the definition of affine stack is a little bit more complicated, and Tohen has a characterization of affine stacks over a field, depending on the using conditions about the homotopy group sheaves being basically locally free, being vector spaces. We're interested in the relative situation. So in the relative situation, the whole picture in general will be more complicated, but we have this strictness property for logarithmic connections with nilpotent residues. And due to that strictness property, we can actually just use affine stacks whose homotopy group sheaves are locally free O modules. So when we start with a semi-stable morphism and we have this special strictness property of the residues, then all the operations are going to be strict, so they're going to preserve it. You know, if you take kernels and co-kernels and so on, those are all going to preserve the property of being a bundle and preserve the nilpotent property. So any operations that you do in the process, you have to do a bunch of operations in the process of defining the representing homotopy type. Those all preserve the strictness, and so they're going to preserve the property of being locally free O modules. Then, so just a little bit of history. The schematization of the homotopy type was defined by Tohen in his paper Affine Stacks, and then studied by Katsarkov, Pontev, Tohen, who put a Hodge structure on that. But actually, if X is simply connected, and that was destined to treat the non-simply connected case in large part. If X is simply connected, then the schematization of the homotopy type is just the complexification of the rational homotopy type. So you could, if you're familiar with rational homotopy theory, you can just take the Q rational homotopy type, just sort of tensor with C in the sense of, for example, using any of the models, the Sullivan model or the Quillen model, et cetera, just take those differential graded Lie algebras or algebras or whatever, and tensor with C, okay? But in a more stacky viewpoint, we can also view these as the universal affine stacks to which the space X maps. We can use the same type of universal property to define a representing object. I'm going to have a diagram on a later slide. In the case of the Durham-Dolbeau or logarithmic Durham stacks, then you need to prove something to get the representability of the functor in terms of an actual homotopy type. And you might say the easiest case of that, or the basic case of that, is if we assume that H1 of the stack is equal to, with coefficients in O, vanishes, then you can get representability. And if you're in a relative case, then, as I said before, we'll use the nilpotency of the residues and the resulting strictness properties to define these things. And I think this was in the Affine Stacks paper, in Tohen's Affine Stacks paper, a simply connected complex schematic homotopy type is equivalent to the various kinds of models such as DGLAs, CGGAs. So now suppose we have a relative n stack, which was one of these relative affine stacks and so on, over the logarithmic Durham stack. Then the restriction to any one of the strata becomes an action of this abelian subgroup of the Lie algebroid, which is to say it's the residue. And this gives us a situation which is very analogous to the situation of the higher Kadeira-Spencer classes, which is to say, as soon as this residue space has dimension bigger than 1, then you're going to get possibly higher homotopy coherence structures defining the action of this abelian thing. Okay, and this is going to arise for us when we have a semi-stable family. The semi-stability condition means that the map is given by monomials where every coordinate function of x appears in at most one coordinate function of s. And so we also said before that the semi-stable reduction theorem for higher dimensional base and higher dimensional fibers was proven by Adiprasito, Liu, and Temkin after an initial kind of weak semi-stable reduction theorem of Abramovich, Karo, and then Abramovich, Temkin, Wodarczyk. And this tells you that after making ramified modifications of the base and birational modifications of the total space, we can assume that our morphism has a semi-stable model. So it makes sense to study the case of semi-stable fibrations as a model for the local topology of a general fibration. Of course, that's I mean, you have to be, take that with a teeny grain of salt since we did these ramified coverings of the base. So you're not really looking at homotopy over any subspace of the base. You're just looking at homotopy over subspaces of the base, which are really local in the semi-stable model. So, you go to pull back to the semi-stable model, and then you look at points that are nearby to one of the strata of the divisors. That's what we're aiming to look at. So suppose we have one of these things. Then we have the relative formal groupoid, which comes with logarithmic Durham formal groupoid. And it comes with a descent to a formal groupoid over the Durham stack of the base, okay? And so we can look at the relative schematic homotopy type of this thing. This is the universal object fitting into a diagram like that. So it's the universal object over S, which this object T is supposed to be one of these affine stacks over S, affine N stacks. And that's supposed to be universal for maps from this thing, which is not an affine N stack at all. I mean, it's a weird stack with all these little infinitesimal attachments and stuff. But maps from this thing into an affine N stack, you can show that under the hypotheses that I said before, you can show that there exists a universal object. And since it's universal, it has a descent down to the logarithmic Durham stack of the base. And in particular, it means that you have an action of the residue space on the homotopy type of the fiber. Now, what does it mean to have an action? It merely means that you have a fiber sequence TR over for degree 1 Eilenberg-MacLane space of this additive group thing, and whose fiber is the TS. Okay, and it's this TR which is the action. Okay, now suppose we have by taking transverse slices, we can always reduce to the case of a zero-dimensional stratum of the divisor. Then the fiber upstairs is going to be normal crossings variety. The fiber of a semi-stable family over a deeper point in the stratification of the divisor on the base. It has a slightly complicated combinatorial structure, right? Because it's not really just a divisor with normal crossings. I mean, it's a kind of iterated divisor with normal crossings. It means take a divisor with normal crossings and then take a divisor with normal crossings inside the divisor with normal crossings and so on. So you need to look a teeny bit at what that structure is. But you're going to have restricted Lie algebroids over the strata of upstairs. Those will glue together in some way along closed subschemes in this normal crossings picture to give the relative logarithmic Durham stack. And then the fiber over the base is the affine stack homotopy type representing the non-abelian shape functor. Then we also have a corresponding topological picture where you just take the link around the divisor, which is a small torus. You have the smooth complex variety, the topological space, which is a fibration over the sphere. We can schematize those homotopy types to get just a rational homotopy type with an action of the pi 1, the local pi 1. Okay. Now, if we assume that the map is relatively unconnected, then this schematic homotopy type is the Durham homotopy type is also the Durham homotopy type. And now we have two different homotopy types, either the base, the TS which is the logarithmic Durham homotopy type over the 0 point, or we have the nearby point. And they both have actions of a C to the K, which is to say of a group of an abelian group of order K. And so in order to say what I'm saying here, we need to use the hypothesis that the actions on the homotopy group sheaves are nilpotent. And this is going to be true for the semi-stable family, which is basically Alan Lamnett's paper thesis. Then using this hypothesis, we get this strictness property. So the homology groups and homotopy sheaves and everything are locally free. Then you can do the same thing as for the case of just vector bundles of logarithmic connection, which is to say you can create a model for the homotopy type. You don't do it by exponentiating this amount, but we can call this the exponential. You can construct this relatively easily, really, by just taking the projection from the Dram stack into the Island-MacLean stack and just pulling back the central fiber. Okay. Then the theorem we can show is that there's an equivalence of categories between the one connected schematic homotopy types over the logarithmic Dram stack and the ones over just the residue space. And so our representing logarithmic Dram type is going to be equivalent to the model one that we just described. And you can show as a corollary, I maybe need to do a little bit extra work, but these two actions on these two homotopy types, one is the action on the nearby fiber coming from topology, and the other one is the action from the logarithmic Dram space stack of the residue on the fiber over the origin. Those are equivalent. So yeah, that's the theory. The proof is, the proof is really, once you have all this language in place, it's basically works automatically. So let me just say that we can use just mention a couple of further directions. So I haven't been talking about the Hodge filtration, but of course we would like to do the Hodge filtration, and we would like to really, in the end, have some kind of Clemens-Schmidt exact sequence type of a statement. We'd like to compare the residue thing and the Kadir-Spencer class. Another question is that whereas in the Kadir-Spencer case, you could calculate an example where there was trivial primary action of the Higgs field and non-trivial secondary classes. I don't actually currently have an example, although I did notice there was a paper that discussed that, maybe. But yeah, I don't currently know of any examples of this in the residue case, so it would be good to look for those. Of course, it would be nice to be able to say something in the case where there's a fundamental group and then we have higher stacks over the moduli spaces of local systems and so on. The comparison statement. I mean, it's really unclear what's gonna happen, and that was really, you might say, the limit part of our discussions with Ludmil and Tony on the non-abelian Clemens-Schmidt exact sequence. I mean, you like to combine the higher homotopic picture and the degree 1 non-abelian cohomology picture. Anyway, so I think I'm done here. So thank you very much.
Okay, thank you. Questions? Carlos, I have a question. So in this story, so back to the Pi1 story. So you have a natural metric on the moduli space. So this have a Kerr metric. Is there any good metric in this story? In this higher homotopy thing?
You mean in the case of simply connected? That's actually a good question, which I didn't think about really. What does it mean to have a metric? Okay, so in some sense, this is related to the question about non-abelian mixed Hodge structures, because the Hodge metric, in the case of a variation of Hodge structure, one way of thinking about the Hodge metric is as it's obtained by using the Riemann bilinear relations with the relationship between the Hodge filtration, the symplectic structure, the real structure, and so on. If you sort of combine all those together, you get the Hodge metric. Okay, in the case of a pure variation of Hodge structure. In the case of a variation of mixed Hodge structure, already just in the abelian case, it's less clear what kind of metric you can really get on variations of mixed Hodge structure. So I'd say maybe, I mean, of course, I think it's a good point is to try to look for the metric or try to look for some or maybe various metrics. But maybe a intermediate step is to try to understand the mixed Hodge structure on these pictures. And we know that there's a mixed Hodge structure on the rational homotopy groups. And from what we said in the paper with Ludmila and Tony, you can also try to define a mixed Hodge structure on the representing homotopy type, the rational homotopy type in sense of higher stack. But of course, I mean, we didn't study that. We tried to define it, but we didn't really succeed in studying it too much. So you'd like to maybe start by looking at the mixed Hodge structure. Then there should be some kind of maybe shifted symplectic structure or shifted Poisson structure type of thing happening clearly. Yeah. So I mean that would be I mean that's the type of direction you could look at, I think. But yeah.
Okay, thank you. Okay, I think it will be last talk will come. So let's thank Carlos once again. Okay. So the last talk is by Professor. Okay. Good. The speaker of our last talk is by Professor Zhang Gaoyong from New York University. The title of his talk is the Minkowski problems, Brun-Minkowski inequalities, and monoampere equations. So let's welcome.
Okay, first, I would like to thank Professor Yao and the organizers for the invitation. So I'm going to talk about so-called convex geometrical analysis. The topics I'm going to talk about is Minkowski problems and some geometrical inequalities and Mosampere equations. Here it's spherical Mosampere equations. Now this conference has at least two themes here. It's 80th birthday of Liang Simon and the proof of the Calabi conjecture. Actually, this is the second time I met with Liang Simon, and I talked with him during the conference. The first time I met him, that's in Australia several years ago. Larry Tudinger and Xujia Wang, they organized a conference also on geometric analysis. So I gave a talk in that conference. So I took some photos. Here's one photo. You may find it interesting. Here, it's Liang Simon, and here is Larry Tudinger. This is Fosco. Probably you know the other guy. I talked with him. I forgot his name. Sorry. So this during the conference, there was an excursion to a park. This is on the boat I took. The second photo I took at here is Liang Simon, and I talked with him during in the park, and it's kind of a tradition in Australia. You touch some animals here. It's a koala. You can touch it. So Liang asked me, "Can you take a photo for me?" So yes, I can take a photo for you. So here's a photo. So I got the invitation to this conference. I knew Liang Simon, and I took a photo. So I digged my photo. All those photos here is what I found. Happy birthday to Liang Simon. Calabi, I talked with him many times when I was a postdoc at UPenn, unfortunately, I didn't have any photos with him. But here I quote a comment of him about the Minkowski problem. This is a classical Minkowski problem. Yeah, so yeah, you can see what's the meaning of this paragraph. Yeah, I give you 1 minute. You can read this. So he mentioned the Minkowski problem is like a Rosetta Stone. So probably you wonder what's a Rosetta Stone. Here is a Rosetta Stone. So it's created in 196 BC, discovered in 1799. Rosetta is a place in Egypt. So found that stone. This stone is very important. It's a key to decipher ancient Egyptian scripts, because here there are 3 parts here: top, middle, and the bottom part. The 2 parts on above here, that's ancient Egyptian script. Usually, yeah, people don't know, don't understand. But the bottom part is ancient Greek. All 3 parts, they describe the same thing, this exactly the same thing. Now, because you know this ancient Greek, so from this you can understand what's the meaning of the top 2. So that's, you know that's why I call it's a key to deciphering ancient Egyptian script. So what's the meaning of this? I mean, I can, yeah, we can try to understand what's the meaning of Calabi said. So the classical Minkowski problem is very important. And it's like a Rosetta Stone. There's some other problems that are very similar, maybe in other subjects. But because you know this Minkowski problem, you know all the method to solve it, that then you apply the same ideas or at least some kind of ideas to solve some other problems using similar approaches. Yeah. Then because of this, I try to say understand what the Calabi conjecture, the Calabi conjecture. This is also the part of the conference. So I have a question: what problem motivated Calabi's conjecture? So yeah, Calabi, I didn't ask him this, and probably Professor Yao asked him, what's this? What's the answer for this? Yeah. So I'm going to talk about convex geometric analysis. So I want to explain abstractly what's the meaning of this. So we study convex bodies in Euclidean space, study the geometry compared to differential geometry. Convex geometry is quite different from the approach. First, the objects, convex bodies topologically is very simple because of convexity. However, differentially, from the analysis point of view, it's non-smooth. That then it's complicated. Also, the philosophy of study here, usually in convex geometry, because of non-smoothness, we can't take derivatives as you want. So most of the time we take integration. That means in convex geometry, we study the geometry, we study it from the global point of view, then come to the local things. It's a reverse in differential geometry. Usually you study curvature locally, then you get some global properties. Here, it's completely the reverse. For example, here we start with so-called, for example, volume surface area. From those things, we evaluate them as geometric functions. Then we try to differentiate those things. Then we get some local invariants. The local invariants we get they are geometric measures. So what's geometric measures? You can think them as curvatures in differential geometry. That's a counterpart of it. Then the three things are connected here. I'm going to talk about the Minkowski problems, their geometric equations, how to solve them. Those things are connected with, actually here, the equivalent to some geometric inequalities, so-called Brown-Minkowski inequalities. And both of them are connected to the PDEs. Those PDEs here, the Mozambique equations on the unit spherical. Now, first I'm going to give you three examples. The first two examples are classical. Everyone probably here, you know. The third example is more recent. Actually, it's not completely solved yet. After this, I will give you an abstraction. Exactly what is, called a Minkowski problem abstractly. Then from that formulation, I will give you three classes of Minkowski type of problems from different, two from the convex geometry, one from integral geometry. Also, I will mention some unsolved problems. Here's the first example. This is classical. It's Minkowski posed in 1897, and he solved it. So what's this one? Suppose you give some positive numbers, f1, fm, and some unit vectors, and you ask the question, can you find a polytope? Here, you just think it as a polygon. Can you find a polygon so that those vectors are the unit normals, outer unit normals, and those positive numbers are exactly the length of the polygon. Yeah, similarly, in the space, you can ask the phase areas, if the phase areas are the given numbers. Yeah, this is a very simple question. Yeah, of course, in the plain case, probably you can solve it. You can just use some simple construction. Here, you can draw a polygon. Say, you first in one direction you draw a length, in another direction you draw a length. Then you show that when you at the end you will get a closed polygon. Then you need a condition so that it's a closed one. What's the condition? The condition is this condition. Yeah, actually it's an if and only if condition. But in 2 dimensions, very simple. However, if you go to 3 dimensions, it's not easy. You can't do this easily. You need to solve some problems, optimization problems for this. That's the first one. Second example, that's the differential geometry. Also, that's first studied at Minkowski. So that's probably you know here. Also, you give a positive function on the unit sphere. Then you ask, can you find convex surfaces close to 1 so that its Gauss curvature is this function? Here, you will use Gauss curvature as a function of the outer unit normal. Then if you just write down this equation in terms of a function here, h actually it's a support function. It's from, suppose the origin is inside. From the origin to the tangent plane, the distance is called the height function or support function. Then you just compute the Gauss curvature, you will get this. This is a reciprocal Gauss curvature. Then you have the equation. This is a Mozambique equation. That's why the two are connected. Of course, this is classical. That's the first two. Yeah, it's solved by Minkowski, and however, that's a weak solution. So you have a convex body, but the smoothness or the regularity is a hard problem. It took a very long time. Yeah, first in 3 dimensions, started by Nierenberg, then in 1976 by Chen Yao. They solved this regularity problem. Yeah, there is a general problem. You can combine the first the discrete one and the continuous one, so that the equations you can formulate as a geometric measure. This is called the surface area measure. Yeah, I'm not going to get inside of that. You just think about the two cases. One case, this is the reciprocal of Gauss curvature. A discrete case is the face area of the polytope. It's like a discrete measure. Yeah. In fact, these two are equivalent. Suppose here you have a unique solution of this. Then you can use this to show that the classical Brownian-Minkowski inequality is true. Also, the proof of this general problem, for example, the existence, it comes from this inequality. So Alexandrov gives two, for example, he gave two solutions. One that's a direct variational proof. You know, variational proof, you need to have shows a variational structure. That means you have to differentiate the volume. To do that, you need a mixed volume theorem. So you need this inequality to show you can differentiate the volume so that you get the Euler-Lagrange equation. That equation gives you what you want. So I'm not going to explain the detail why the two are equivalent. I just want to point out the two, they are equivalent. The importance of this probably the better known inequality is this isoperimetry inequality. I believe everyone should know this inequality here. So this one is stronger than this. You take air as a unit ball, then you differentiate this, you get this inequality. So this is a special one of that. Now the third one, the first two are classical. The third one is more recent. It's called the logarithmic Minkowski problem. So you, very similar to the first problem, you start with some positive numbers and unit vectors. But here you don't ask the length, you ask the areas of the triangles. You ask if you can construct such a polygon so that those triangle areas are exactly the positive numbers given in advance. So you want to solve this problem. So here it's the geometric equations, a system of geometric equations. Now, how do you solve this? Actually, for the general case, this is still unsolved problem, even in the plain case, what I stated over here. If you assume that you work on symmetric polygons, that means centrally symmetric polygons, this problem is solved. You need to have some properties of those numbers, the so-called concentration of measure. So also, I'm not going to get into the detail of that. The measures constructed here using those triangle areas in space, that's cone volumes. From the origin to the face, every face you have a cone. Those volumes, you can construct a volume, a discrete measure. So that discrete measure, it's called a cone volume measure. This is a special case. It's a paper published in 1993. So Lutak posted this problem, so LP problem. This logarithmic one is the case p equals 0. That's why we call it is a logarithmic Minkowski problem. And in 2013, we solved the even case, the general even case. But in R2, it's still unsolved. Singular case, it's hard. The discrete case, there is a continuous virgin. The continuous virgin is it's similar to the classical one. That's easy to solve. Yeah. For the continuous case, there is a equation. Let's call it the logarithmic Mozambique equation. It's this. If you compare with the classical one, here you have an h. The h on the denominator, you know that when you solve such a Mozambique equation, usually you need this side. It's bounded from above or bounded from below, right, away from zero. So here you can say if h is approaches, if the convex body is flat, so here h is small, then it's not bounded from above, right? Yeah. So anyway, it's bad when you have an h on the denominator. Yeah. The existence is easy to solve. However, the uniqueness of this equation is harder to solve. So here is the unsolved uniqueness problem. You can assume that f is a smooth function, any smoothness, will be okay. Say infinity. Then you ask a question. Here you assume it's even. Now we care about the even in this case. You ask if the solution to this equation is unique. This is an open problem. I think it's a major problem in convex geometry. Probably, I'm not sure in PDE, probably, it should be because it's this is a geometric problem. It's a major problem in convex geometry. I believe in PDE it should be a very important problem. You try to solve this uniqueness problem. Yeah, it's important because suppose you can solve this problem uniqueness. Then from here, also together with what we proved, the existence from both, you can prove this so-called logarithmic Brown-Minkowski conjecture. This is true. Why this is important? Because this one is stronger than the classical one. I mentioned the classical one in the previous slide. Yeah, here, the classical one. This is a classical one. Yeah, classical one. Now this side, you change it to, this is a user linear combination. Here, this is called the geometric combination. That's a smaller. If you put a smaller one here, you ask if it's still true. So if this is true, that implies the classical one. Yeah, this so-called logarithmic Brown-Minkowski conjecture is a major conjecture in convex geometry. People usually ask me what are the most important problems. The number one unsolved problems in convex geometry. I would say, most people will say, oh, Mahler conjecture, that one. Then you ask the second and the third, the different answers. Maybe a slicing problem, but the slicing problem already just solved very recently. Then this problem, I would rank it as the second, probably the most important unsolved problem in convex geometry people care about. There are already some conferences in convex geometry people devoted to just this problem. Yeah, so many people worked on this one here. For example, here I just mentioned some name here. Newman here, some Chen Huang, and some other people. After this abstraction, I want to give, after the example, I want to give you the abstraction. So what is a Minkowski problem usually here for geometric measure? You start with some geometric invariant, some important geometric invariant, for example, volume, surface area, or some others. Say here, I call it W, that's some geometric function. Then you differentiate this. This geometric function, it's a differential, usually can be represented by some geometric measure. That geometric measure is M and K. Yeah. It's like what I mentioned before, the surface area measure, cone volume measure, some others. Then the prescribing problem of this geometric measure is called the Minkowski problem. You give any Borel measure on the unit sphere, you ask him, can you find the convex body K so that this geometric measure is the measure you given? Yeah, it's given. If you usually, when you rewrite this in terms of differential equations, it may be this kind of equation. And because of this, you require this, there may be a Brown-Minkowski type inequality associated with this. So that's reasons together. Here is a geometric, it's a variational structure, the construction of geometric measure. Here it's a PDE equation here. Here is a geometric inequality. The three are related. So that's the abstract one. Then you can, yeah, we can describe, say, three classes of Minkowski problems. The first class is classical. Yeah. This class of problems, you start with the so-called intrinsic volumes. Yeah, so here, this is a sequence of geometric functions. The first one, yeah. The first one is the volume. Yeah. Yeah, so the second one is the surface area. Then you have some others. For example, the last one is the so-called mean width. Anyway, they are the important geometric functions in convex geometry, in particular in the so-called mixed volume theory. Now, how those things are defined? They define this way: you have a convex body, you project to a plane. Depends on the dimension, because it may not be the -1 dimension, maybe no dimensions. Anyway, when you project, then you average those volumes of these shadow areas of the projection. Yeah, then you get a geometric invariant. It's called the Kermas integral or intrinsic volume. Then for those geometric functions, you differentiate this, you get a geometric measure. This is called as a area measure. That's proved by Alexandrov. I mean, first defined by Alexandrov in 1937. Then you ask the Minkowski problem. You give a measure, you ask, can you solve this equation, this measure equation, find the convex body K? Yeah, the I equals n case, that's a classical Minkowski problem. That's the first example I mentioned. The I equals 2, that's the Christoffel problem. Why is Christoffel problem? Because those area measures, if it's continuous, then its density, that's exactly the reciprocal of the symmetrical functions of principal curvatures. So they are related. However, now for this problem, the uniquely is solved. The hard part is the existence. So from I from 2 to n, the existence is unsolved problem. Why is can't be solved in convex geometry? Because the variational structure, we don't have variational structure. What I mean here? Now this is the differential formula. That's the variational formula, differential structure. However, you can see here, I put a t equals 0 plus here. It's a plus. There is a plus. So we can't remove the plus. Because of this plus, that means the function is not differentiable. It's only one side differentiable, right? Now then you can't use the variational method. So you have an optimization problem. Say it's differentiable. Then you differentiate this. You get a Euler-Lagrange equation. But here you can't. Why? Because of this. You don't have the other side. That's why this problem is still unsolved. unsolved. I mean, this is a main reason. Then people can try to solve this using purely PDE method. Yeah, that's for PDE method, not many results. In 2003, it's Guan and Ma, they use the PDE method follow what did before Chen Yao's paper. So they use a continuity method. They gave sufficient conditions. Yeah, this probably, I believe there is probably the best one known up to now. The second one I want to mention is the Minkowski problems, the dual from Minkowski theory, also from convex geometry. Now this is approach from a so-called dual approach. The first class I mentioned, it's from the projections. When you have a convex body, you project, you construct some geometric invariants. Here, you do the intersection. So you have a convex body, you intersect by planes. May not be hyperplane, maybe no dimensional. When you project and when you intersect here, you get the cross sections. Their areas you average, you get some new geometric invariants. Also, they are very basic in convex geometry here. Now, again, you follow the abstraction I described. You try to differentiate this those geometric invariants. Now, for this one, it's very lucky. When we differentiate this in here, actually, we can do better than the classical one, the classical Christoffel-Minkowski problem there. Here, there is low plus. T is 0. That means those functions here, it's different from the projection ones, the intrinsic volumes. Here we call that dual volumes. They are differentiable. So those geometric functions, they have variational structures there. That means we can use variation method to study those problems. I mean, these problems here. Yeah. Here, the detail of this formula here, K sub T, it's not exactly the one like the other formula here I mentioned here. Yep. This is a plus. That's when you can have this, that means that when T is positive, this is well defined. If T is negative, this is not defined, not well defined, because when one convex plus here minus here, if here you minus T, when you subtract, you don't know if this horizon is convex or not. So you don't have the convexity. That means here it's not true. Yeah. So here, to get the convex one, you have to use a so-called Wolf shape or Alexander body. You construct the envelope of some function. Here is the function we used from starting with support function HK. You do this variation, then you find the largest convex body, so that the support function is in this. Yeah, is in this. So we proved this formula. Actually there is a case I equals n. When I equals n, this is classical. This formula that's proved by Alexander Loff in 1938. As I mentioned earlier, Alexander Loff proved this formula. This is the formula I equals n. That's the volume. So he proved the formula use the geometric inequalities, use Minkowski inequalities, use that theory to prove this formula. However, for those geometric functions, we don't know those formula and those inequalities. That means Alexander Loff's proof doesn't work here. We proved this directly because that's in fact this is the formula only the second formula in convex geometry for the variational formula. This kind of thing. After Alexandrov proved the first one for the volume. Then for others, for those things, we proved that's 70 probably, yeah, many years later can prove this. Not many such formulas in geometry. Yeah. Now for this construction, you can also follow the abstraction I mentioned. You can study so-called dual Minkowski problem. For the geometric measure, this is so-called the dual curvature measure. You ask if you give me a measure, can you find a convex body so that this dual curvature measure is your given measure? And there is a Mozambique equation attached here. That one, it's like this here. Now, there is a little more over here. That's the gradient of H. This gradient is in the Euclidean space. Yeah, this side is on the Euclidean sphere anyway. This is easiest to write. Yeah, some problems associated with this problem. Several cases of existence already solved. For example, when case symmetric, that means mu is even. The problem is solved for many cases. Again, the uniqueness for this problem is unsolved. If you can solve the uniqueness problem, then you can prove some geometric inequalities very similar to the one I mentioned before, the logarithmic conjecture here. Yeah, those are the extensions of that. Yeah, there are lots of people studied this problem here. I just want to mention some names, and it's a long list. Yeah, those two are from the convex geometry. Now the third class of problems that's from integral geometry. So we try to find some invariants, geometric invariants, and to study geometric measures. So the third one, it's called chord integrals. It's from integral geometry. In integral geometry, I believe the first then, and from the classical, usually we consider random points, right? Points is a point in the space. The integral geometry, the long trivial then, why? Yeah, you study it's you have random lines, not just the points in the space. You have random lines in space. So here, this could see that's a random line. If I have a random line, you intersect with a convex body, you have a chord. Now you do this integral. We call this a chord integral. Yeah. If the power is Q, then here you have an IQ of K. Yeah. Now this is a family of geometric invariants. Also, it's closely related to the user geometric invariant, like volume and the surface area. In fact, when this Q equals 1, that's the volume. When Q is 0, it's the surface area. And when Q equals n plus 1, yeah, that's that you get the volume of square. Yeah. For other cases, there are no such formulas. So you can think of this family of geometric invariants or chord integrals as the interpretation of the surface area and the volume. So we want to do the same. Can we reconstruct the geometric measures from those chord integrals, those integral geometric invariants? Yeah. Fortunately, this class we can also do the differentiation. Yeah, if you differentiate this, you get a formula. Yeah, get a formula. That's by the Ritz. Yeah, if abstractly, by the Ritz representation theorem. This is a linear function. After you linearize this, you get a linear function. Then you have a geometric measure to represent this. Yeah, that geometric measure. Yeah, we have to prove what is this. Yeah, it's a geometric measure. Yeah, we call this a chord measure. Yeah. The proof of this it's like the one I mentioned before. It's not that easy, not easy to prove. Yeah, you have to have some specialisms. Once you have the geometric measure, we call this chord measure. Then you can pose a chord Minkowski problem. You ask this problem. Very similar. Suppose you have a spherical Brownian measure mu. You ask, can you find a convex body K? So that this chord measure is your given measure mu. Given measure mu. Now, this chord, there is also a PDE associated with this chord Minkowski problem. We call this chord Mozambique equation. It's this equation. This side that's like other cases, but it's this part. Now this part, this G, it's not really a function for H and delta H. It's not that kind of function. This is just implicitly dependent. So actually this function is given by this one. Yeah, this kind of raise integrals, right? Yeah. So also depends on this. When you have a function H, you can construct this so-called Wolf shape with a convex body. You construct this, then this is inside. That means you do this integral over this convex body here, because this is a characteristic function. This is when Q more than one, this is the integral is inside. When Q is less than one, the integral is outside. Yeah, there's some unsolved problems associated with this. Again, the uniqueness solution, the uniqueness of solution is unknown. We don't know what is this. Also, the regularity of the solution also it's unknown. Yeah. So for this Mozambique equation, we don't know what's the regularity of this. Yeah, maybe the PDE people, yeah, can solve this problem. Yeah. Yeah, this is very different from the classical one. Classical one, G is a function of H delta G. It's explicitly given, but here it's not explicitly given. It's implicit here. That's the hard part of this problem. Yeah. Again, if you can solve the uniqueness of the solution, then you can prove the so-called Koda-Brown-Minkowski inequality. So those geometric invariants, the chord integrals, they have geometric inequalities, Brown-Minkowski type. We can prove that. There are some other Minkowski problems. Yeah, here I'm not going to get talk about. I think 3 examples are enough here. 3 families are enough. Yeah, I want to end my talk. So the subject of Minkowski problems, this subject, yeah, it's a main part of the so-called convex geometric analysis. Again, I quote what Calabi said in his MS bulletin review. This is the last sentence he wrote in that same review. He said, this subject, Minkowski problem, is a beautiful subject in YT. Current research is active and the new results are appearing very rapidly. I'm not sure that's the case in differential geometry, but it's definitely the case in convex geometry. Recently, with my quadrants, we wrote a survey paper on Minkowski problems, also published in the Bulletin of MS 2 years ago. It's called the Minkowski problems for geometric measures. If you want to know many other Minkowski problems and whole picture of the subject, you can look at this survey paper. Yeah, all right, thank you very much.
Okay, so thank you, Professor Zhang, for your last talk. Are there any questions?
Hey, thank you for the talk. Can you formulate these Minkowski problems over like a convex subset of the sphere rather than the entire sphere, some boundary value problem?
Yeah, there's some other people they consider those kind of them. Yeah, definitely.
So there are
some studies.
boundary value problem versions of
right.
maybe another question. Like which one of these are like invariant affine under affine transformations?
Oh, affine transformation, the one logarithmic one, it has some affine invariance there.
It has some, okay.
Right. Also, there is one I didn't mention, the LP problem when p equals n plus. In this case, when p equals minus n, also there is an affine in structure there. Yeah.
Maybe third question. Is it related to optimal transport?
Optimal transport. Yeah, I believe it's related. For example, here, the second one I didn't mention, the dual Minkowski problem. There is one, the classical Alexander-Loff problem is a special case of that. So the Alexander problem, some other people using the mass transportation to give a proof for that problem. I believe probably you can apply similar thing to this kind of problem.
Okay. Thank you.
For the logarithmic Minkowski problem, if the uniqueness is true for smooth data, then is that automatically true for measure data?
Oh, no, it's not true. If it's true for smooth case, that is enough to prove the geometric inequality, but without equality condition. You don't know the extremer.
Okay.
Yeah.
Thank you.
Any other questions? If they're slow, let's thank the speaker again.